Okay, we'll start slowly. Just kind of to recall quickly what we've done the last time. So we started studying the inelastic behavior of the solid materials, and basically said that the proper framework of studying that which allows us to clearly define the main characterization of this type of behavior, which is dissipation. That is the energies that you don't manage to store, is thermodynamics. Thermodynamics being the joint studies of heat transfer and dynamics of mechanics. So you have to kind of extend the description of your problem other than mechanical properties, something like Young's modulus in 1e. You need to have like a conduction coefficient to characterize the behavior in terms of heat transfer of the same material. And then in terms of the computed fields, for mechanics, we have displacement, strain, and stress. And for the heat transfer, we have entropy, temperature, and heat flux to worry about. Now, all this is done to be able to clearly define dissipation, as I said. And then dissipation nowadays is nicely described by introducing so-called internal, or some people call it hidden variables. I call it uncontrollable because basically those are the variables that have their own evolution, which is decided by the interaction between different parts of the solid body. And basically some of the characterization that we studied are plastic deformation, for example, in particular, but we also see today viscoplastic deformation, damage variable, and so on. We also looked into hardening. So I said what that is. It's basically plasticity, meaning that you have a reversal deformation. Viscoplasticity might be the same, but with a rate dependency that gives you like a different response. And finally, damage implies that you have a change of the elasticity modulus. So basically, we introduced in thermodynamics was the study of the heat transfer, and I also showed you the time integration schemes that are applied to first principle thermodynamics for heat transfer part that simply amounts to very well-known heat equation. Basically, it says that internal energy is conserved or changed by the basically heating. And then you go to more general framework of the thermomechanics, and then the internal energy is changed not only by heating, but also something called stress power, product between the stress and the strain rate. Then we studied different potentials, and we actually said that at the end, if you have internal variables, these different potentials could be used interchangeably by using Legendre transformation. And the key point is at the end, you have to supply the evolution equation of internal variable. So we started supplying such equation by studying this is type of equation that you have, like C alpha being internal variable, and it has to be defined as a function of this state variables. In particular, here for Gibbs potential, this is a stress and temperature, and also internal variable itself. So we started studying that by looking into so-called rheological models that could be introduced by studying a simple one-dimensional problem and simplifying the problem to a unit length of a bar and unit cross-section, in which case you can directly obtain stress-strain diagram by studying usual boundary problem. And so we started with linear viscosity to define a viscous deformation, then which is kind of the simplest model that you can introduce, but also not very usable for describing the behavior of real material. And then we look into viscoplasticity a little bit better to describe the same type of behavior and clearly indicated what actually should characterize the evolution of this internal variable. And that is the case when you actually have much faster evolution of the internal variable with respect to the state variables like stress, temperature, or strain, whatever it is that you want to choose. Depends on the choice of the potential. So if you want to make sure that you really have very fast evolution, you go to rate independent plasticity, or the simplest version of that is so-called perfect plasticity, which is simply a series connection between an elastic spring and a frictional slider with the limit of elasticity equal to sigma y. And for this one, we described in particular how you actually obtain the dissipation as the product of the stress being the conjugate to the internal variable, which is here plastic strain. This is the sliding of this frictional slider. And then we obtained the stress strain diagram for this particular case, and also learned how to use it in terms of the let's say evolution equation that can be obtained from the yield criterion. And particularly this yield criterion is also like a potential that allows us to obtain this rate equation, and that follows from the principle of maximum plastic dissipation. Now, this principle has just confirmed what we obtained directly in 1D, but now this principle can apply in a more general setting. 3D case, for example, where it's really difficult, if not impossible, to provide a corresponding rheological model. So we have recovered the same evolution equation. And finally, the final step is when you're plastic, you want to, for example, know that you keep getting the plastic deformation, in which case this allows you to say that the derivative of this criteria in time should be equal to 0. And that allows you to provide a value for this gamma. So for the elastoplasticity, it was a very simple case. It is like stress is linearly proportional to the strain or it's constant. And then we made it more interesting to be closer to real type of behavior by introducing linear hardening and then explain the same steps to apply and also explain how to get computation with the finite element method. So the key point here was when you use finite element method, then you use the standard let's say technology of the finite element computation, where you switch from a physical domain to a natural coordinate domain, making each and every element look the same if they belong to the same family, like a two-node truss bar and so on and so forth. At the end, thanks to an idea of Bruce Irons, we are using numerical integration, and that means, for example, for two-node truss bar element, computing all the values in 0. So this is really very significant saying for plastic behavior, because that would imply simply that the plastic deformation and hardening variable are needed nowhere else in terms of this element, but at the Gauss point. That's the only place where we need the stress, and for the computational stress, we need this variable. So that reduces the storage of these variables very significantly. Also, the other point is the plasticity in one element is completely unrelated to a plasticity of another element. Relation of these two things will come only through the global equilibrium equation, when finally the element which is yielding, that's actually becoming less stiff, is through the equilibrium equation saying to the other guys, I can no longer take this load, so I have to unload. So here somebody should be able to take it instead of me. And that's really the idea that actually follows into this type of computation. So we carried out this computation saying that we have a single step scheme that we already studied for a heat transfer problem, which is simpler because there's no constraint evolution. Here, the main difficulty, we do have a constraint evolution in the sense that the stress should be plastically admissible. Namely, the yield criterion should be always either negative value or 0 value. It can never be positive value. This is simply not admissible. So in order to comply with that, we tried the explicit scheme, but we found that it's quite difficult because the three equations that we're using, which are evolution equation for plastic deformation and hardening variable, are unrelated to the equilibrium equation, which is the last one, supplying displacement and total strain. So combining three fields which intervene in computing the stress and checking plastic elasticity, which is the plastic strain at n+1, hardening variable at n+1, and the total strain at n+1, there's no way you can be sure that you are really matching this. So for that reason, you need implicit scheme. And implicit scheme, given that you have two very different groups of equation. On one side, you have a local equation for each and every Gauss point of the element which is plastifying. On the other side, you have like a global set of equilibrium equation that is providing the total displacement values, and that allow you to compute the total strain value. So these computations are separated. We call this operator split, because operator which allows us to compute the values of the unknowns that we are trying to find, that is plastic strain, hardening variable, and total strain, is actually partitioned into the global part and local part. So the global part, we start with kind of best iterative guess. In the increment analysis, you take the one from the previous increment, and then you run the local computation for each and every element, each and every Gauss point independently. And then basically the goal of this computation is provide the plastic strain for the given the best iterative value of your total strain. So there are two cases. The step could be elastic, so it's easy computation, or the step could be plastic. So basically, if it's elastic or plastic, you kind of provide corresponding value of stress by correcting if it's plastic or not correcting if it's elastic, and then corresponding value of the tangent modulus, either for the 1D elasticity to be Young's modulus or product of EK divided by the sum of E and K, K being the hardening modulus. So then we go back to the global step and we recompute the total displacement with the next iterative guess. If the residual is not small enough, it is, we stop. And then we go to the next step and so on and so forth. So this is the way we can compute this type of result. Then I quickly covered also that if you go to 3D setting, and if you use the boldface letters, which are now hiding a number of components, in theory 3x3 components of strain, 3x3 components of stress, and 3 components of displacement, you can write the basic ingredients of the plasticity in 3D, which is the additive decomposition of the total strain tensor into the elastic strain tensor and plastic strain tensor. That means that each and every of these components of the strain is split additively, so you can have an elastic shear and plastic shear and so on and so forth. Now, for different materials, not all strains will be triggered, but this way we have generality to treat really like the most general setting that you can possibly imagine. So the second ingredient to provide the potential, if you quickly copy the case of one-dimensional problem, the only thing we are now using boldface letters to describe the strain with the 3x3 components. And also instead of the elasticity tensor, elasticity modulus, Young's modulus E, you're using elasticity tensor C, which in 3D case, given isotropic homogeneous linear behavior, for the elastic case, you need at least not only Young's modulus, but you need the Poisson's ratio. And then hardening is also generalized with some kind of vector type of hardening variables and the corresponding tensor for these hardening modulus that you generalize. Then you go into the third criteria is the third ingredient is the function. They say that the function of stresses, of stress tensor, and then do variable to these hardening variables should be always negative or 0. So in the elastic process, you can say that you can compute your dissipation that looks very much like the one that we had for 1D case. In other words, you have like a stress multiplied by the plastic strain, and then you have a Q variable, the dual variable multiplied by the hardening variable rate. So basically, in the elastic case, this dissipation is equal to 0, so that allows us to obtain the constrict equation for the stress, which is partially due to our potential. And then for the plastic case, we know the plastic dissipation has to be positive, and the goal is now to compute corresponding evolution equation, which you can obtain by the principle of maximum plastic dissipation. So this gives you this tensor type evolution equation. That is the rate of the plastic deformation tensor is proportional to gamma dot plastic multiplier multiplying d phi d sigma. So d phi d sigma will be some kind of tensor. You'll see in different criteria what kind of shape this will take. And then also the evolution of the hardening variable psi dot will be equal to gamma dot times d phi dq. Of course, this has to be submitted to the loading and loading condition, which is the third equation you get from this optimality condition by taking the derivative of the plastic multiplier. So you get back with your phi that has to be equal to 0 for the plastic case or negative for the elastic case. So in fact, what I try to show you is that in 3D, when you take this tensor-like notation, the equations are identical, really. It's just we use slightly different letters, and even if they are same, they're both as opposed to kind of normal letters, but the structure, the reasoning, the procedure is exactly the same. What gets more complicated is just more details. In other words, one should not be discussing with these details. So for example, here, loading and unloading condition. For this 3D case, this is illustration, the directoric plane, the plane which is perpendicular to hydrostatic axis. For example, for von Mises criteria, which we'll start with, basically we are talking about circle. So whatever is inside the circle, it's called elastic. What is on this circle, it's called plastic. And what starts going outside is not plastically admissible, unless you have hardening, in which case the circle will be expanded. So basically, in this case, you have elastic loading or unloading. The loading will be if you stay inside the circle, or if you start shrinking the circle. Plastic loading will be if you start extending the circle. And then here you have some kind of a in-between case, which is neutral loading, where you can be tangential and so on and so forth. Then the computation of your elastoplastic modulus again follows from a consistency condition, namely you go with a plastic case and you assume that the T plus dt, that is the next step, you should still be plastic, in which case phi dot should be equal to 0. That allows you to compute your plastic multiplier that would allow you to keep plastic admissibility of the stress. And then finally, you can have an elastoplastic modulus. You can see that elastoplastic modulus is so-called, let's say, rank 1 update of this elastic modulus. you have this term which is C d phi d sigma. There's all the product with a C d phi d sigma, and this is the scalar value, which is normalizing for that. So we'll see now this for the first plasticity criteria, which is heavily used in many of these books that I mentioned. This is a criteria for Mises. Turned out this is the criteria which is the most suitable for metallic type of materials, the type of materials that characterize the first industrial revolution when you were building the things like, you know, a big ship like Titanic, which finally sank and so on and so on. So basically, the observation that metallic type of materials like steel, aluminum, and so on and so forth are really weak when you apply a shear force. Goes back to Tresca, and he has a postulated criteria, which is nowadays called Tresca criteria, which says when the maximal shear stress reaches a certain value, limit of elasticity, then you will start plasticity. However, we'll go back to that one eventually, a little bit further in this lecture today, and this leads to something called multi-surface plasticity. In other words, you have three different values of principal shear stress. This could be simply computed as difference of principal axial stresses. Let's say the principal shear stress 1 is sigma 1 minus sigma 2 divided by 2, sigma 2 minus sigma 3 divided by 2 is the second, and so on and so forth. So basically, these are like three different surfaces. That's why you call it multi-surface. And for computation, sometimes, you know, people before didn't figure out what to do with it, so it wasn't very practical. So for Mises, who was a German mathematician rather than a physics person, and he realized that the shear stress is actually, a shear strain is related to the change of shape. And what is characterizing the change of shape is the rhetoric part. So the rhetoric part of stress is used instead of these shear stresses. It came down to a very similar, if not the same type of criteria, but it could be described with a single surface. So then this is the kind of criteria that people kept using with Fontaine's. So basically, since you have a change of shape expressed with the rhetoric type of stress, it becomes really like a very simple to handle. You only have one type of mechanism that shows, and it's almost like if you take this tensor notation, you go back to kind of features that you already recognize in one case. So it's not only like in terms of formulation, but also in terms of computation, you recognize many steps and they become basically identical. The only difference, you know, what we had here, the elastoplastic tangent modulus in the continuum case and the one discrete case, contrary to 1D version, is no longer the same. And that was like a big deal result that was given in the work of Seymour and Taylor, and took many years to put it into code. So that allows you to have a quadratic convergence of Newton's method, having this, etc. So we'll comment about that as well. Now, if you want to extend the predictive capabilities of for Mises criteria, you have to take into account hardening. And basically, the type of hardening that were taken into account was due to the works of Prager, Drucker, Ziegler, types of kinematic hardening, allowing to take into account the Bauschinger effect. That means when you go reverse the order of the sign of the stress is no longer the same type of threshold. So these things we'll kind of discuss as well in terms of refinement of the model that we're talking about. And then normality rule with this, that follows from a principal maximum plastic dissipation was also something that goes back to works of Samanan, Levy, and so on and so forth. So let's see what this criteria should be. As I said, for Mises, figured out that you can take the rhetoric part of the stress. What is the rhetoric part of the stress? Well, you take a stress tensor, which is 3 by 3 matrix representation, and you take a trace. That means you sum up the components which are on the main diagonal. So this will be your trace of sigma. It's a scalar. You multiply this by unit tensor, which has 1, 1, 1 on the main diagonal and 0 all the other, and divide it by 3, and then you subtract this from the original stress tensor. And this is what you call the rhetoric part. That happens that the rhetoric part is conjugate to the change of shape, whereas the trace part divided by 3 is a pressure, in particular is something like hydrostatic pressure. It's conjugate to the shape, to the change of volume. So you can always characterize, we already said that when we were talking about elasticity in 3D, you can characterize behavior of elasticity in 3D for isotropic material with two components, see the Young's modulus Poisson's ratio, or take Lame coefficients lambda mu, or you can take a bulk modulus. So this will ratio between the hydrostatic pressure and change of volume. And you take a shear modulus, which will be a ratio between the rhetoric stress and the change of shape. So this is the kind of thing for metals that we're going to be using. Basically, you need, let's say, shear modulus to characterize behavior, and you need the rhetoric stress. Now, we can compute the principal values of this deleteric stress by usual procedure that you take a deleteric stress minus lambda being the principal values times the identity times the principal vector equal to 0. And then the condition of having this so-called characteristic equation solution that would be determined that this should be equal to 0. So this could be written as the cubic equation in lambda. In other words, you have these three values, lambda to the power 3, J2 lambda plus J3. Now, J2, I mean, this equation should be invariant, whatever is the coordinate system that you are using, because the eigenvalues are always the same, no matter what is the coordinate system you're using. And so basically, J2 happened to be one of these invariants that feature into the characteristic equation. And this could be computed as the norm of the deleteric stress. What is the norm? You take the deleteric stress, you write it down, sigma 1 deleteric, sigma 1 2 deleteric, and so on and so forth, until sigma 3 3 deleteric. You multiply each component by itself, you sum it up, you take a square root, and that's it. Now, when I said this as introduction, then I can give you what was in these books, what it still is, if you have one, or from Hill or whatever it is, Mandela and stuff like that. There's all of a sudden, instead of a yield function being absolute value of sigma minus sigma y plus k psi that we had in 1D case, in 3D case, mysteriously, you have a normal deleteric sigma compared against square root of 2/3 of sigma y plus k psi. So what the hell is this square root of 2/3? Why does it come? Well, basically, we can study the one-dimensional type of behavior by taking into account, let me maybe take this as a small illustration. So I can basically take a simpleton test to get what is a illustration of my. So this would be like I have a fixed here, and I'm imposing some kind of imposed displacement in this particular direction. So 1D model would allow me to characterize this with the corresponding values of the hardening and so on and so forth. In other words, the only stress component is equal to sigma. And then when you have this deformation, again, you're going to have this extended to some kind of a deformed shape. So I would keep it like that. This will be your deformed shape. You really extended it a lot. So this is at the first stage, this is the second stage, and then you kind of unload and you realize that your stuff is never really the same as that used to be because you crossed the limit of elasticity. So if the length of this one is equal to 1, this will give you your plastic deformation. Otherwise, it will be plastic deformation times the length. Now, this will be like a 1D interpretation of the type of loading program that you have crossed here, then you kind of harden, then you unload it, and you're here. So this is your plastic deformation that I'm putting in this picture, okay? Now, I can also take this to be a real physical type of a specimen, which has certain length and certain width. And we said, again, we are kind of deforming this guy. In reality, what really happens is at certain point, it will undergo so-called necking, where the one part of the section will become significantly more narrow. And basically, it's really this shear band that you can start seeing as the way of behavior of this type of material, not one dimension. But we are interpreting this in this manner. So for this particular case, I have my sigma, which is a stress tensor, and it has only one stress component, which is here. If I took my x-axis again in this direction, and so this is my sigma 1 that I simply call sigma, and all the other guys are equal to 0. So I won't go writing them. Well, some of them, if you want, okay, there, and then all the way down. So all the other guys are 0. So, okay, what is now the deviatoric part? First of all, trace of sigma is simply you sum up sigma plus 0, so it's sigma. Trace of sigma divided by 3, this is basically sigma divided by 3. So the deviatoric part of sigma is simply you subtract this one from that one, so you're going to have like 2/3 sigma. Here would be minus 1/3 sigma. and minus 1/3 sigma. And all the others are 0. Okay, so this is it. So basically, if I now ask that yielding will start in the same way like in 1D, I want this component to be equal to sigma y. So here's the only component that becomes sigma y. Then I go to my filter, which is called the rhetoric part of stress, computing the rhetoric part of such a stress tensor. So this becomes 2 sigma y over 3 minus sigma y over 3 and minus sigma y 3. So I said the norm is nothing but you take each and every component and multiply by itself. You sum it up and you take square root. So that becomes 2/3 squared plus 1/3 squared times 2. This is what's written here. So that becomes basically you pull out sigma y, and here's left 4/9, and here's 2/9. So 2/9 and 4/9 is 6/9. You cancel by 3, and that becomes 2/3. So automatically, by following the same rules, that you have like asking for the stress to be equal to sigma y, like you had in 1D case, you have this filter square root of 2/3. So there's really no physics that is new. There's no, let's say, phenomena that is new. It's just the way that you are quantifying the behavior of the material, that you take into account all the possible components and so on and so forth. Now, this is the type of thing that justifies why I have square root of 2/3 with 5 sigma y. Just one remark. I don't have to have only simple tension tests. When I was in the École Normale Supérieure, we had a maître de conférence. This is like a, in principle, temporary position that you keep for a certain number of years before you do habilitation, then you become professor, in which case typically you leave that university, you go to another place. So that actually happened to one young guy to whom we wanted to help. And we bought this testing equipment, which had a very thin cylinder. And so it turned out that for some reason, in the maître group, they liked obtaining the yield stress not by the simple tension test, by torsion of the cylinder. So if you apply torsion of the cylinder, assuming the cylinder is very thin, you say that the only stress that appears there is the shear stress. And then you can ask that the shear stress goes to sigma y, to the yield, and happens that such a stress tensor is already rhetoric because there's nothing in the main diagonal, so trace is equal to 0. So sigma is the same as the rhetoric sigma. So if I take a norm of such a rhetoric sigma, it becomes square root of 2 times sigma y. In other words, when I report the stress, not only I should say what exactly is the value of the stress, but I should be saying how did I actually obtain it. Otherwise, you kind of have the problem that if you really misinterpret what you're really doing, that will be the case. Okay, then I said I also want to justify why I have a square root of 2/3 multiplying this hardening part. So we said the hardening part is actually the let's say the norm of the plastic deformation. In other words, I can take hardening as integral from 0 to t, rate of the plastic deformation, which will be always positive, and I here multiply by square root of 2/3. Why? Well, because the idea is that plastic deformation, according to these rules that you already studied in detail, will be obtained as a gamma dot, the plastic multiplier, times the derivative of phi with respect to sigma. So phi is proportional to the rhetoric sigma. The derivative is equal to the rhetoric sigma divided by the norm of the rhetoric sigma. And this is something called the unit rhetoric tensor n, which is, let's say, orthogonal to this rhetoric plane. And basically, the trace of such a tensor, given that the tensor is rhetoric, should be equal to 0. Hence, this gives me the plastic strain rate. And if I sum up all the plastic strain rates, multiply by the incremented time, I get my plastic strain. So basically, the idea is that whatever I write for the plastic strain, it has to be written such that you have trace equal to 0. In other words, if I want to do like I did in this 1D case, measuring plastic deformation in the direction load that was applied and call this epsilon plastic, then in the two transverse direction, I should have, assuming isotropy, minus 1/2 of epsilon plastic and minus 1/2 of epsilon plastic. And this way, I'm sure that these two guys are actually matching the plastic strain tensor and making it incompressible. Because in J2 plasticity, plastic deformation is incompressible. So if the plastic deformation much bigger than the elastic deformation, which is the case in many practical applications, I have behavior which is called quasi-incompressible. And we'll see that that requires a special handling of the finite element interpolation, otherwise you get in trouble. again, the method of incompatible modes that we talked about is very useful, but you have other type of interpolations as well. So this is the reason why I actually had to have this square root of 2/3 for two different reasons, but happen to be the same factor, so it really simplifies the type of writing. So, okay, in any case, what I've done is a plasticity with, let's say, linear hardening. I did not change any rules other than 3D point of view or 2D point of view on the situation which is developing. So basically, then I can simplify my general expression that I obtained for general plasticity. And in this particular case, I have my hardening variable evolution equation, psi dot equals to square root of 2/3 times gamma dot. And plastic strain is already mentioned, and gamma dot is equal to n is the rhetoric unit tensor times epsilon dot divided by 1 plus k divided by 3 mu, mu being the shear modulus. So basically, this is the type of thing that I have, and the loading and unloading conditions are, again, elastic unloading is if I'm already sitting on the plastic surface, I could be entering anywhere inside the region. And then plastic loading will be I'm trying to expand this plastic surface, in which case they should be orthogonal to this surface there. Neutral loading is again a case that I might run into and I have to be able to handle. And this is the just remark, and you have it in the book, that if you have a continuum setting, the stress rate equation will be written this way. That is, elastic part is simply elasticity tensor times epsilon dot, whereas elastoplastic part, you have this rank 1 update of the elasticity tensor. However, in the discrete setting, what is really done is first you have to discretize. In other words, you have to take into account all the equations that you are using when you're doing your time integration scheme with the operator split and so on and so forth. And then you linearize to get really the true elastoplastic tangent modulus in discrete setting. And you can see that these two results are not the same. Namely, in the discrete setting, we have an extra term, which is all the way here, which actually allows us to have truly quadratic convergence property of Newton's method. If you neglect this one, you do not get this quadratic convergence anymore, unless you have very, very tiny time steps, because in this case, gamma, which is equal product between h and gamma dot, because of h going down to 0 will kind of be negligible, and you will recover the type of tangent modulus here. So initially people were using very small steps, but once you understood what to do, and you use implicit scheme, then you can do bigger time steps. And for those cases, it was really important to include this part here. And so this is just a numerical computation. Anyway, if you don't have tangents which is correct, you should be again able to converge, but you need many more iterations. Unless you want to be more efficient, this part is very important. So, as I said, this could be pictured in 1D, and this could be pictured in 3D. That looks like a 1D. If I here plot the diagram, the rhetoric part of the strain tensor versus the rhetoric part of the stress tensor, this looks very much like my diagram for 1D case. I have a linear analysis, I have linear elastic response here, which is now given not by the Young's modulus, but the shear modulus. Then I reach the yield stress, and then I go on my hardening part this way. This could also be pictured in the rhetoric plane. Imagine that I was here, in which case you have a circle of certain radius that corresponds, let's say, if you're yielding for the first time, corresponds to this yield stress. And then you go into the hardening part. First, you get a trial step. You go outside of this, and then you realize your trial value of the yield function is positive. So you have to kind of reduce value and project back. But also in this step, if you have hardening, the circle will expand due to the hardening variable, because the radius becomes not only sigma y, but becomes also k plus psi at this particular step, psi being hardening variable. And so basically it comes down, illustration as follows. Here's the center of the circle. And then basically you simply have a radial projection from this trial state into the center of the circle, and you get this point. So this could be certainly used to accelerate the computation of this final state in terms of this plasticity. So that was really like the main reason why this model was so favored to many people, because it turns out to be very robust. You cannot go wrong. All these circles, if you have isotropic hardening, are just getting bigger and bigger due to the hardening. And then when you're projecting, you come back and they're all concentric, they all have the same center. So if you go outside, you just project down to the center and you find this point in one shot. without any difficulty. So this is the kind of illustration you can have, but still it's a 3D plasticity, but illustration as such that you clearly show that there's only one mechanism there. Now, as I said, if you take, let's say, 4-node element, you will have to do something special. You cannot handle plasticity just with the basic 4-node element. I'll show you with a couple of examples that to be the case. First of all, how you actually build this type of element. First, you build your total deformation field by using displacements at the nodes, and then shape function that you do for computing interpolation. In particular, for the total strain, you need these B matrices. For each node A, you have a derivatives of the shape function NA with respect to either x1 and x2 to compute the corresponding strain components. So this is one type of computation that we have to obtain at each and every Gauss point. Now, on top of this computation, I have to keep the values of the plastic deformation, hardening, or psi. We also use the Q, which is, you'll see the backstress. If you have a kinematic hardening, we'll get to that in a second. And all these values have to be stored for each and every of these points. So you have to have access in your memory to the values that are stored there that could be handled over the typical time step. You have to have values that are time tn, and then new values that are time tn plus 1. So typically, when you have time step scheme, and you are a one-step scheme, you're kind of converging in a particular step. You then keep the values at n plus 1, and you erase these at n, and you go for the next step, and so on and so forth. You don't really keep this memory forever. You just take it as much as you need it for a particular computation, this time step. Now, I said it cannot be simple as a parametric element. And here's one of these very famous examples, because this is one of these few cases where people who are working for a software company. He's an Aktagal, and maybe Parks is also this guy, who worked for Abacus company. He's one of these well-known people who created Abacus software. And then Abacus software at a certain point in time was sold to Dassault System, who was the owner of Katia. So now they call it, I think, Simulia, whatever it is. So this is, Rice is a well-known professor at Harvard, one of the few engineering professors who did lots of things in fraction mechanics. So basically, they wanted to interpret what happens to a type of fracture or this double-edged notch specimen. So this is a simple tension test, but the specimen has these two notches to make things kind of more interesting. What is making it more interesting is typically the notches lead to stress concentrations and typically accelerate the failure. So the analytical results of Rice was available. So he gave us let's say, the control value of such a case by using the method that are typical of his type of knowledge. And then Naktagal was computing this with the isoparametric components and plasticity with the Abacus code. And so basically, we reproduce this type of test by taking into account the symmetry. You only take a quarter of the specimen. So you have like a symmetry type of condition here. You have also this condition here. This is left free. And here you're pulling your stresses. So basically, you can see that if you take a displacement method, which is here in French model déplacement, you keep climbing up there. Basically, you kind of lock, and you do not get this typical load. There are some remedies to this. If you take reduced integration, that would mean that you take a single point for the, let's say, a volumetric part and 2 by 2 for the electronic part. You get somewhat better result, but still not good enough, because 4-node element still remains only rather poor with bilinear interpolations. But if you add incompatible modes that we discussed already in 2D case, basically you start getting really like a nearly perfect result, because you get rid of the locking phenomenon. This is really this case that I was discussing, because here you have a support, here you have a support. So due to the incompressibility, you can see up here, plastic deformation is much more large than the elastic deformation, because if you unload and you follow this straight line, your elastic deformation is like a fraction of a plastic deformation. So your behavior is not incompressible, which would lock this completely, but it's so-called quasi-incompressible. The change of volume should be close to zero. It's not zero, but very close to zero, or the magnitude smaller than the change of shape. And unless your finite element interpolation have this ability, there's no way you can represent that. So incompatible mode interpolation would have that, because incompatible mode allow this element to kind of breathe, to accommodate to this. Whereas as a parametric element, we already studied that if you have this something, you know, that this is locked, this is locked, this is locked, and then you have incompressibility, this node cannot move. So now this is quasi-incompressible, so it barely moves, but not much. So you really kind of lock, and you cannot do it there. It's even more obvious if you take something which is not only plastically incompressible, but also elastically incompressible. Namely, you take a Poisson's ratio to be close to 5. This is 0.4999. And then on top of that, you put plasticity. So either you run that in the computation, which is using axisymmetric elements, or you run that with the computation by using plane strain elements of a quarter of a cylinder, and you can have the results here. Now, these are your isoparametric elements. They have a order of magnitude smaller displacement because, again, they lock because both elastic and plastic incompressibility are here. So it really, locking is very severe. And if you have like a incompatible mode, basically you can have a really right on the curve. You can try this one of these cases. You can compute this analytical solution. I think you have this in the book of Lubner, this type of computation. Now, if linear hardening is not good enough for you, you say that true behavior is something that really is not just linear. You go back to this picture. This was the real behavior of the real material that motivated our. So that certainly is just not straight line. It could be something that basically you start having, let's say, nonlinear behavior, and then you kind of have a maximum stress that is so-called saturation point. And after that, you go down failure. So basically, if you want to fit hardening in a better way, not just by linear hardening with a single hardening modulus, and you want to be modest, you start with the two type of components, you can go for a saturation hardening, which is the case here. So instead of just yield stress, I can also use something called ultimate stress. This is the maximum value of stress to which the material will saturate. And then I can multiply the difference of these two, sigma infinity minus sigma y, by 1 minus exponential minus beta times xi. So what that does, that actually spreads this in the exponential type of fit. And basically, you kind of recover this type of nonlinear behavior that you have here. So beta is another parameter you might want or might not want to put that allows you to go faster or more slowly into the spanning the difference between sigma infinity and sigma y. What is changing now here? Well, when we had the linear hardening modulus, the computation of the plastic multiplier was a simple linear equation. It was a phi n plus 1 trial divided by E plus K for 1D case, and something kind of similar for the 3D case. We just had it here. Gamma dot is equal to this guy. It's a linear equation, so K is constant. Now the problem with the saturation hardening, K keeps changing for different value of the level of stress. So the fact that this is let's say a convex function, if the saturation goes, the saturation goes in this way, we can now work it out, bring all these equations. When we realize that phi n plus 1 trial is positive, we now have to solve the problem of these two evolution equations and the yield function to be equal to 0, with unknowns to be plastic strain, hardening variable, and plastic multiplier. So we take these two evolution equations, plug it into the last equation, which is now nonlinear, and that one could be written as a divatoric part of sigma n plus 1 trial minus square root of 2/3 sigma y minus qn minus 2 mu gamma n plus 1 minus 2/3 of qn plus 1 minus qn, and q being a nonlinear function of this. And you can say that this function is very nicely set to the Newton's iteration, because it's like taking it upside down. You start with gamma n plus 1 equal to 0, and basically you're kind of converging very quickly. This is actually the idea. Let me maybe I can illustrate what I'm talking about. If you have a saturation hardening, now this is your sigma epsilon. So you have until limit of elasticity linear behavior, and after that you have this kind of nonlinear behavior that goes into the sigma infinity. So this thing here is a convex, maybe not perfect pitch, sorry about that. And then when I'm computing this one here, this is my gamma n plus 1. And this is my phi n plus 1. So I'm starting with the gamma n plus 1 trial equal to 0. And I have my phi n plus 1 trial. And this equation that I wrote, so this is a trial value. It's really like this type of curve, but only put upside down. And then eventually it crosses. So we are looking for this value of gamma n plus 1 to define a value which will make phi n plus 1 equal to 0. So you're taking Newton's iteration like that, and it's almost perfect for this type of exercise. So basically, this is the kind of thing that we are using. We need several iterations to get down to the final value of gamma, and that's the only extra computation that has to be done, and you are set with the nonlinear isotropic hardening, which might have a better prediction for post, let's say, elastic response. So this doesn't increase computation too much, and what's also important to say, you want to make this local computation so robust that, because this is the kind of computation the user should not be intervening. So you want to make sure that every time you're computing your gamma, you converge to the finest precision that you want to use, because this would then condition the plastic admissibility of the stress and so on and so forth. So basically, this gives you the possibility to include the isotopic hardening. On the other hand, if you have a cyclic loading, what people found out many different ways is basically if you take a cyclic loading and you want to really represent a type of behavior in plasticity. So this is your stress strain diagram, this is your epsilon, this is your sigma. So you start with a linear behavior until sigma y. And then I can go like that if you want. And you go there. So this is now a threshold of plasticity. So if you unload, if you have this isotropic hardening only, you're going to go to the same level as this height here, only for the negative value of sigma. However, in reality, many materials do not behave this way. There's something called Bauschinger effect. And then yielding starts much sooner. So start already here. Obviously, this value is not the same as that, but something did happen. So basically, people introduced something called kinematic hardening. They said, okay, it's like, the origin of the elastic domain has been moved. And then basically, you can then start yielding at the same distance, like from this origin to the top. And then you can produce much better hysteresis loops as you go along and produce that. So what is it really needed? Well, in this particular case, I don't use any isotropic hardening. I stick with the kinematic hardening only. My yield condition is written as a divitoric part of sigma plus Q, where Q is so-called back stress. Back stress, to be in agreement with the divitoric part of sigma, should be divitoric stress. So the trace of Q is equal to 0. And I don't take any isotropic hardening, so I compare this against square root of the third sigma y. And then my plastic strain rate would be equal to gamma dot times n, where n is now computed as the divitoric part of sigma plus Q divided by the norm of the same tensor divitoric part of sigma plus Q. So basically, this is the model of Prager-Ziegler for the kinematic hardening. And you can introduce also the sort of kinematic hardening proportional plastic deformation to be written as a gamma dot times n, and that you can compute this way as a gamma dot times d phi dq. So other than the composition of the total strain, I have to provide the energy. So the energy, if you have kinematic hardening, could be written again as the quadratic form of the elastic strain. This is 1/2 epsilon minus epsilon plastic dot c epsilon minus epsilon plastic plus h divided by 3 times k dot kappa dot kappa. Here we actually took this to 2/3 because it's indeed to combine with the final result, and 1/2 or 2/3 of h and so on and so forth is just convenient writing. The reason for that is when you kind of group it together, for some reason this is kind of a choice which was made. So I can compute my thermodynamically conjugate flux to the kinematic hardening, that gives me this, what you call it, the Dirichlet back stress. And basically, I can compute for the linear hardening case the final value of gamma n plus 1 if I have a tri-value to be positive. And also you can see that the elastoplastic tangent modulus, which has a modification because of this hardening phenomena, and it's not the same as the continuum case, which will be only the case here. So this is also the modification that you might want to use for increasing the predictive abilities of your elastoplasticity model. So we have done everything for the elastoplastic models. We started with the one which has just a linear isotropic hardening. Then we've done something with a nonlinear isotropic hardening. Then you could do kinematic hardening. If you want to do both, there's no problem whatsoever. You can just put it up and you have more internal variables. You have to compute more, but the more the merrier, what they say. And so that we like the same with the rate independent plasticity. This is kind of final work on that. One of my doctoral students, Lotfi Shofi, was working out on this cyclic loading plasticity and basically used something called the Frederick Armstrong, or in Francis called the Chabosh model, for which you have a really wonderful hysteretic slope that you can control in terms of stability and kind of always keep the same value as we go along. And we were able to get the quadratic convergence. You can see that when you go down to zero, the number of zeros goes doubling and so on and so forth. Now, if you want to have a rate dependency, we can go back to viscoplasticity, and I want to show that the philosophy of obtaining the different steps is pretty much the same. There's only one difference when we go down to the principle of maximal plastic dissipation. I'm actually not using the constraint minimization, but actually using the penalty version. So these models of viscoplasticity are very well known in the previous works or in UK and in France. Maybe the most prominent versions are the one that was done by Pergina, who worked with Hill. So that's why it's for kind of big exposure. And then the other one was in the book of Georges Duveau and Jacques-Louis Lyons, where they wrote it also as the part of regularization of the plasticity. Jacques-Louis Lyons was a mathematician, so it's one of the few books that the mechanics persons, the collaborative math, where they put lots of development from mathematics and this regularization and so on. So it's a kind of very typical for many courses that mechanics people did in France, and there are lots of kind of mathematical development and so on and so forth. When you come to physics, of course, you have to follow a lot of math, and if you don't know this math, then it becomes kind of tough. Anyway, the idea is if I want to go to viscoplasticity, what will change? First of all, the deformation that is irreversible is no longer called plastic, but it's called viscoplastic. Other than that, the total strain is still split of the elastic strain tensor and viscoplastic strain tensor. That didn't change. And both of them are infinitesimal. That means the components are smaller than 10 to the minus 3. So this is the first ingredient. Second ingredient, again, is my potential. So if I don't worry about any hardening, we already learned about all kinds of hardenings. I take only the so-called perfect plasticity for 3D version. This could be the free energy would be like elastic minus viscoplastic strain. So it's just elastic strain. This is total minus viscoplastic dot elasticity tensor times the same strain, elastic minus total minus viscoplastic. And basically that allows me to compute that sigma is equal to C times epsilon elastic when I have elastic case. Then final step is instead of the criteria, I still have the criteria which says that phi is a deviatory part of space minus the square root of 2/3 times sigma y. But this time around, contrary to plasticity, I say that when phi is negative, is elastic, but when phi is either positive or zero, it could start being a plastic, or viscoplastic, sorry. That means the novelty is that I allow the value of phi to be larger than zero, and I no longer have constraint. So any stress field is admissible, and the more you violate, let's say, the elastic domain, the larger will be like viscoplastic deformation. Now, I need this notion of something called Macaulay bracket. This is x in these brackets that is actually x plus absolute value of x divided by 2. That is equal to x when x is positive and it should be actually 0 when x is negative. This is a mistake. So why do I need that? Basically because I'm going to appeal again to the principle of maximum plastic dissipation, but this time around, rather than introducing a plastic Lagrangian, we introduce the constraint by Lagrangian multiplier, which is becoming then plastic multiplier. I'm simply saying that I take a penalty version. In other words, on the function that I'm minimizing, which is here, the minus viscoplastic dissipation, the product between sigma and elastic viscoplastic dot, I add a quadratic term, which is supposed to be penalizing this type of thing. In other words, you know, I'm looking into, like, I'm coming down to a corner, but instead of corner, I put it into that kind of quadratic form. And that's actually the choice that I made. Is the choice that basically I want this p to be positive and x is positive and 0 otherwise. So one simple choice is to be 1/2 x squared. And then basically to have this one here. So if I take a derivative of such a function, where this is 1/2 x squared when x is positive and 0 if it's negative, derivative of this function becomes x when x is positive and 0 when x is negative. And that's precisely this Macaulay bracket. So in mathematics, and this is in the book of Duo and Lyons, this is called Yoshida regularization. So you have to handle the things in a kind of, let's say, easier way because you remove the constraint. And then basically what's reassuring here, when you push viscosity down to 0, you should be able to recover the kind of thing that you have in rate-independent plasticity. So if you want to keep the computation in a pretty much the same manner, there's a trick to write your evolution equation for the viscoplastic deformation, epsilon viscoplastic dot, in this fashion here, what follows from the minimization of this regularized part of the viscoplastic dissipation. And basically that becomes 1 over eta times the positive value of phi, which is fulfilled by the Macaulay bracket, times d phi d sigma. So let's say the direction of the viscoplastic deformation is the same direction of plastic deformation. The only thing gamma dot in plasticity is obtained by imposing phi to be equal to 0, in which case you have to kind of do separate computation. Whereas here, as long as you have your stresses and your viscosity parameter, you can obtain immediately this kind of viscoplastic multiplier. In the code, you can actually very easily implement both plasticity and viscoplasticity, just say which version you're computing, and then you can obtain your multiplier in the most appropriate way. So basically, this will be the story about viscoplasticity. So I learned how to get different hardening phenomena. I learned how to get rate effects. And I've done almost everything what is possible to do with von Mises criteria. You can also get like a nonlinear elastic response on top of that, and you have it in the book. You can check on that. But I'll switch now to the different type of criteria, because as I already said, historically, the first criteria, which was really quite credible understanding what is the problem with the elastoplastic behavior of metal type of material, was Tresca. And Tresca said that the metals are yielding when the maximum or principal value of shear stress reach yield stress. So the one shear stress is 1/2 sigma 1 minus sigma 2 compared against sigma y. Then second shear stress is sigma 2 minus sigma 3 compared against sigma 2i. And finally sigma 3 minus sigma 1 compared to sigma y. There's also the kind of criteria with the multi-surface, where actually these are like different surfaces, if you want to think of that. Or some people call it non-smooth surface, where you have corners. And so basically, you have similar criteria for a cohesive type of material like soil or thing like that. Rankin was a very well-known professor in Glasgow working on this soil mechanics problem. So he proposed criteria where it says that the principal of sigma 1 reaching yield stress, you get yielding, and then principal of sigma 2 reaching yield stress, you get yielding, and principal of sigma 3 reaching yield stress, you get yielding. And so in this case, what really has changed, not much. I still have a elastic plus plastic deformation to be total deformation. I still have a free energy, and instead of one criteria, I now have a bunch of them. So when I go down to dissipation didn't change. The fact of what is the criteria doesn't really matter. For example, for plasticity, it's still sigma times epsilon dot. And the only difference is that now that I have many of these constraints that I have to impose. So theoretically, I can, if I go back to rating then plasticity, I can define my plastic Lagrangian as a minus plastic dissipation, which is sigma times epsilon plastic dot, plus the sum of all these constraints, multiply each and every one of them with the particular plastic multiplier. So I have 3 constraints, I have 3 plastic multipliers. So what's the catch? Basically, the idea goes as follows. Let me illustrate that on a Rankine type of criteria. So you said the Rankine type of criteria is the one that you can present in a derivative plane. So this is the plane that is perpendicular to the hydrostatic axis. This is my principal stress sigma 1. This is my principal stress sigma 2. And this is my principal stress sigma 3. So you're looking at, from the hydrostatic axis there. And so basically, if you take Rankine criteria to be P1 to be they call Phi1 was absolute value of sigma 1 minus sigma y less than or equal to 0. That means I simply take a straight line and I put it over there. So whatever is below, this is the value of sigma y. Whatever is below, this is elastic. What is above, it's plastic. Then the second criteria is Phi2 equal to absolute sigma 2 minus sigma y. That be now the straight line that's perpendicular on this one. So it's always perpendicular here. And the final one is you take the straight line, which is perpendicular to that one. And basically you're here. So this is your illustration of Phi1. This is illustration of Phi2. And this is illustration of Phi3. So when you're computing the let's say optimality condition for the Lagrangian, which is equal to a minus dissipation plus sum of all these 3 plastic multipliers times Phi1, 2, and 3, each one multiplied by its own multiplier. The problem goes as follows. Imagine if you are here at time Tn, this is your sigma n, and then you jump up there, this is your sigma plus trial, n plus 1 trial. So basically you jump out of this one and then you're simply projecting back normally. So your sigma n will be here. So in this case, and I'm not taking into account any hardening type of, if I did, this would actually move up and so on and so forth. So basically the idea, this is my final sigma n plus 1, which is plastically admissible. And basically in this particular case, the only surface which was really active, which brought me down, is the surface 1. And this is one scenario. Another scenario would have been if I jumped up here, and this was my sigma n plus 1 trial, sigma n plus 1 trial. Then in this situation, most likely, I'm going to get here, and I have to kind of get the normal vector from that guy, normal vector from that guy, to get me corresponding contribution of gamma plastic 1 and gamma plastic 2. So only 2 surfaces will be active. So in any case, there's really no situation where all these 3 surfaces could be active. Simply, whatever is the trial state, it's either 1, 2, or 3 by itself, or 1 with only one of the neighbors that gets activated. And then what happens if you go with all 3? Well, if you go with all 3, the typical situation, you do this computation, it's done this way. Typically, what you do is like you take this a complementary type of a norm, which is sigma n plus 1 trial minus sigma star, the sigma star being the final value of stress. You want to minimize it under this constraint, and then I can obtain linearization to be computed this way. So I can compute the increment of stress over several iteration and the increment of these plastic multipliers for surfaces 1, 2, and 3. So I already said for Rankine illustration, not all 3 of them could be active. There's just no way you can do that. So if you started with all 3 of them being active, the end result will be as follows. you have, for example, the case number 2 that I mentioned, where gamma 1 and gamma 2 n plus 1 will be positive, and gamma 3 n plus 1 will be negative. And basically, you cannot have plastic multiplier being negative because that doesn't make any sense. It's really not in this type of hypothesis. So basically, what you've done, you did an error, and you now know that gamma 3 should be excluded. So start this again, but you kick out gamma 3. And you only start with using gamma 1 and gamma 2, and you have to iterate again. So the fact if you don't know from the start what kind of case you're handling, you can always start with more general case, have it converge, and see which one is positive, kick out that one, and then repeat computation to get the right one here. So basically, it's really the idea is just illustration a little bit better. Whiteboard, and I take existing whiteboard, okay. That would be in here. What the hell is this? Open board. Jacking me too much in. What happened here? Okay. So basically, here I had a gamma, which is like a, you know, I'm going to cover the distance from here to here, and this is sum of these two vectors. In other words, I have a orientation which is d phi d sigma, d phi 1 d sigma, d phi 2 d sigma times gamma. This is type of thing, and then these two that are perpendicular to this surfaces, and basically these two together vectors, they give me the final one, how to stretch it. If I meddle the last one, you know, this will simply enter there and perturb this computation. And plus it will be the wrong sign, because then I will go, if I have the last one, it will, you have to do this, and then you have to do that, whatever it is, and you get it completely merged. You know, so the idea is really that ideally you should know whether you are in front of one of the surface or you're in one of these corners, which is not so easy always to do. We managed to do that in implementation of this type of model. Let me show you what we've done. Instead of Rankin or Tresca, one of my former students was working on the sort of quasi-brittle materials, and we wanted to reproduce plasticity that looks very much like a damage that we discuss later on in this lecture. So basically, the criteria was then done in the strain space, and turned down Saint-Venant was also working on that. So we called it again Saint-Venant multi-surface criteria. So this is done the principal way of the elastic strain. So basically, it said that if the elastic strain epsilon 1 elastic reaches the value which is a characteristic of yielding, then you have a plasticity. Or if you have a elastic strain number 2 reaching the value that you have in yielding, you have plasticity. Then you turn this into the corresponding stress criteria, because you want to find the real format. But let me just comment on that. How we actually did it is this goes as follows. Basically, the idea goes as such. You know, when you have a plasticity, this is your epsilon sigma diagram. And then basically you have a limit of elasticity sigma y. The slope is equal to E. And epsilon y is simply equal to sigma y divided by E. So basically, what was our criteria? We had one axis and another axis. So this is epsilon 1 elastic. And this is epsilon 2 elastic. These are principal values of your elastic strain. We're talking about 2D, so you compute epsilon 1 is always larger and equal to epsilon 2. So the first criteria, phi 1 epsilon, simply means that here is a epsilon y. So whatever is below or right to the left of this line, it's elastic domain. And whatever is to the right, it's an admissible, and what's on this line is plastic domain. Then you have also this straight line, which also built on epsilon y. So this is now your phi 2. And so this is the second surface. But given that epsilon 1 is always bigger and larger than epsilon 2, in fact, what's your elastic domain is simply this point here. So basically, your multi-surface criteria becomes this line and this point, because epsilon 1 is always larger or equal than epsilon 2. And then basically, how do we go to stress values? Well, you write that sigma 1 is sigma 2 in terms of the principal values is equal to a matrix which is called lambda plus 2 mu. If I use lambda parameters, then lambda plus 2 mu. And here you will have the principal values of the strain, epsilon 1 elastic and epsilon 2 elastic. Then given the criterion spread of epsilon, I can invert this equation and get how epsilon elastic 1 and 2 are function of sigma 1 and 2. And then I can go back to what was representation of this, let's say, two functions in the sigma space, or sigma 1, sigma 2. So again, you have like a phi 1 and you have a phi 2. And basically, elastic domain is just this wedge here, because phi 1 should be always larger or equal to phi 2. And these are these two functions. So it becomes lambda, well, I took lambda bar if it's plane stress, plus 2 mu divided by 2 mu sigma 1 minus lambda bar divided by 2 mu sigma 2, minus sigma y should be less or equal to 0. And then minus lambda bar over 2 mu sigma 1 plus lambda bar plus 2 mu divided by 2 mu sigma 2 minus sigma y less than or equal to 0. So the trick is we have to be able to guess upfront whether it's only phi 1 which is activated or whether the trial state will put you into this range, in which case the both of these guys are activated. So given that, it was really able to do that. And then we were able to compute this type of thing for, let's say, plasticity in a rather efficient way. Basically, it was used to study the fire resistance of some kind of masonry structures with the hollow bricks and stuff like that. So I can tell you it was a very defined model for this type of structure, but people who were paying for that needed such a refined model and they were happy with it. Now, this was lots of thing about plasticity. I think whatever you wanted to do, you can find, let's say, an answer here, hopefully. Maybe some more wild thing you wanted to do, but we can all discuss if you need it. But the second type of inelastic behavior model is not only plasticity, but it can also be a damage. So really the damage model and then a couple damage plasticity is an alternative of the major phenomena that you might find in the inelastic behavior. In plasticity, the main characterization of this phenomena is that you have irreversible deformation that you obtain upon unloading. So if you go beyond limit of elasticity, then you unload, you have plastic deformation. In the damage, when you go beyond of the fracture, when the cracks appear, you have a change of the elastic properties. And then basically this is kind of the major type of difference. So initially when people study that, you have references which are probably the most well-known. In France, this is the book of Lemaitre Chaboch, Mécanique des matériaux solides. And in US, this is a guy of Yugoslavian, Dusan Kacino, that I met. He wanted to give me the book, but it's like when he showed me, there was more than 1,000 pages. I said, thanks, I'll pass on that. You know, it's really, really too much, because both of these books are not much about finite element computation. They are simply representation of the model and then different criteria that you might use and stuff like that. But both of these books follow the idea of Kachanov that goes back to 58. That is like a representation of the phenomena of cracking. And so this is some kind of phenomenological model that is placed into continuum mechanics framework that is supposed to represent linear fraction mechanics. Linear fraction mechanics have something like the criteria of this kind is also well established, and there's a whole, let's say, science that study linear fraction mechanics, where you just focus upon crack and you talk about dissipation of fraction process zone and integrals. So when you look into this theory, it's kind of very different from what people do in plasticity. But then I've seen many people are expert on linear fraction mechanics. When they have to do and define a little bit more refined behavior, that becomes a problem. In reality, linear fraction mechanics, you have to have a crack. And then basically, then you study this crack is stable or unstable. So nowadays, there's something called the phase field approach, because basically they took this approach of linear fraction mechanics and they extended it to the same thing. But again, they had to have where the crack is. So I would say this type of theory might apply credibly in the case where the cracks are easily recognized, identified, and then you want to study stability of the structure which already has cracks. On the other hand, if you have a structure which has not had already cracks, and you want to establish, basically the problem is that you don't know where the crack will appear. That typically depends on the subtle combination between the loading and the heterogeneity of your material. And so where you can think that it would appear because of the peak load, it might not appear because material happened to be stronger there rather than the other place. So there's only this uncertainty there. And then what mode will be winning, because different materials don't like shear, some don't like tension, some don't like compression. So you really might be surprised with the composite material, what kind of stress field is the worst for creating the crack. So again, this is kind of uncertainty. In any case, there's another method compared to the incompatible modes method, which is leading. We'll talk about that. I think it's not today, maybe tomorrow, about the bending discontinuity, which allows you to go all the way down to the softening failure. This method is really about extending dissipation into the part of the softening. Contrary to that method, we have something called X. You know, like used to be Twitter, now it's called X, FEM, finite element method. It was first started by Babushka, very famous mathematician. They call this partition unity. And then it was made very popular by Velichko with the XFEM type of method. So this type of method is actually representing the cracks globally with some kind of Heaviside function, which is a jump. Maybe near the end of the crack, you put a special function which are taken from linear fraction mechanics, like what they call fond difficile at the end of the crack. And then basically you kind of introduce this special displacement field. Honestly, for me, I never really understood the predictability of such a theory, because the problem is that typically finite element computation would not give you exact result. Even in 1D setting, unless special case, you don't get exact result. In 2D, 3D, it's practically impossible. So if you're not able to get exact result for the elastic response, to get displacement, strain, and stress correctly, there's no way you can really predict the crack. And then putting crack on top of the finite element mesh, it looks kind of, let's say, kind of appealing, but in fact, really the predictabilities are kind of tough. So before going all the way there, we'll eventually discuss it. I'm just giving you the idea about different type of models, which you can do, and what are the advantages, what are disadvantages. In any case, for some reason, when I came to a corner of my superior in Kashan, where Jean Lemaitre who created it, everybody loved damage. So basically, they did this damage this time. So here's for example, the motivation. Imagine you take a simple tension test with a material which is prone to cracking. First of all, this type of material, like a concrete or whatever it is, you cannot put it in the testing machine, because if you grab it, it will be broken. If contrary to steel, it doesn't have this resistance to be put in the testing machine. But imagine you do intellectual sort of exercise, and you say, imagine if I could do it, what would happen? So you take a simple tension test, and you have like a specimen which has a nominal cross-section A, and if you cross the limit of elasticity, which could be here called the fracture limit, because you talk about cracks, you start having cracks. So you can assume safely that the cracks are perpendicular to the tensile stress, because then start separating. So the hypothesis here is that the crack is immediately leading to a zero resistance. There's no cohesive resistance or something like that. As soon as you have crack, poof, you go to zero. So you stop the test before you completely break the specimen, and you observe, and you can then, by let's say some kind of, again, intellectual process, gather all the cracks, you put them in the cross-section called A bar, and then the area which is not damaged is called A, the nominal cross-section, minus this section of the cracks, A bar. Now the stress which is acting on this non-damaged area, because all the others are zero, they have no more ability to carry the stress. This is called now effective stress. So in 1D case, I can clearly introduce something called a damage variable, as opposed to plastic deformation to be internal variable. Now little d is a damage variable. It's also internal variable, which is going to characterize behavior of this material, which is prone to cracking. So damage variable can be quantified in 1D case as the ratio between the cross-section of the cracks divided by the nominal cross-section. So you have a case where you have not a single crack, where d is equal to 0 because a bar is equal to 0, all the way to you cut the specimen in two, then a bar is equal to a, so little d is equal to 1. So how do we handle now this into computation? Well, you say ability to resist the imposed space and to have the reaction, whatever force bearing capacity of this specimen is basically either I take a nominal stress, which is equal to sigma, and basically I multiply this with a, which is nominal cross-section. Or I take effective stress, sigma bar, and I multiply this with a healthy cross-section, which is a minus a bar. And these two should be the same, basically. And then I can say that the real constitutive behavior only concerns the healthy stress, so basic healthy part. So I can have a effective stress sigma bar is equal to E times epsilon. From this connection between two stresses, that would follow, then the nominal stress sigma is equal to E times 1 minus D times the same epsilon. Hence, I can write this sigma to be damaged Young's modulus, which I compute as E times 1 minus D times epsilon. And that's the kind of way that was introduced. So you can see that as D goes closer to 1, Young's modulus gets weaker and weaker. Initially, this is Young's modulus, and after that, it goes down all the way into 0. Now, the problem with this in terms of computation was really that little d in iterative type of procedure can become even bigger than 1. Then your damage Young's modulus become negative. And we'll see that as we go along, if not today, then tomorrow, that this is leading to something called non-objective response and all kind of trouble. So this was the approach that was followed pretty much by both Lemaitre and Cascino. So we tried to change this approach and to make the damage model look more like a plasticity. But it cannot be fully recovered. There's really the only one major step which is different, and that's the definition of the internal variable. So the only thing which is very simple, instead of little d, we introduce big D. So little d is the ratio between the, let's say, the area of the crack and the nominal area, whereas the big D is so-called compliance. Initially, you will see it starts as 1 over E in 1D setting, and then it can go to infinity. And so the advantage compared to little d, well, little d goes from 0 to 1, and you get in trouble if you go above 1 because you have a negative value of the Young's modulus, the damaged specimen, and you go into softening, so it's not easy to handle this. Here with the big D, it can go to infinity, and then you have no problem handling infinity because anyway in computation, nothing is really infinite, so you have no worries whatsoever. So the only change from what I really discussed before for plasticity is that I no longer have a total deformation split into elastic and plastic, but I have a total deformation computed from stress by multiplying this with the so-called damage compliance. And damage compliance is my new internal variable. As I'm giving you already a sneak preview that starts with 1 over E, and it can go to infinity. And the goal will be to find the evolution equation for damage compliance so I can quantify the change of the elastic response as we go along. Other than that, I'm simply copying what I've done before, maybe changing the names. Before here, I have now free energy. I happen to write it as a function of epsilon and d minus 1, d minus 1 being current value of the damage compliance, d, sorry, being current value of damage compliance. When I invert it, I get current value of the, let's say, tangential modulus. And I can take the same isotropic constant linear hardening with the constant value of the hardening modulus k. Then finally is the yield function that I can call also the fracture criteria, which is absolute value of sigma minus sigma f, let's say a limit of elasticity, now in terms of fracture, minus q. Q being the conjugate variable to psi, which is obviously computed as minus k times psi. So everything is fixed there. Then I sometimes introduce this small change. Instead of starting with the postulating that epsilon is d times sigma, I can postulate the complementary energy in terms of damage compliance to be given as quadratic form as 1/2 sigma times d times sigma. And then basically appeal to join the transformation to exchange the roles between sigma and epsilon, and start with this as the first hypothesis. So then I can go to my second principle of thermodynamics and define this dissipation to be equal to the stress power sigma times epsilon dot minus derivative of free energy plus, this is hardening potential here, psi, uppercase psi or lowercase psi, quadratic form in hardening variable psi. Then I go through this development. I take the computation of this derivative, and at the end I get the final form, which is epsilon minus d sigma multiplied by sigma dot plus 1/2 sigma times d dot times sigma plus q times psi dot. And basically q here is the derivative of this uppercase psi respect to lowercase psi. It's equal again to minus k times psi, given that this guy is a quadratic form. It's like in plasticity. What has changed? First of all, I have elastic process. From this hypothesis that complete energy is quadratic form in sigma, I can obtain back my equation that doesn't have to be postulated. So elastic process actually gives me that epsilon is equal to d sigma, or sigma is equal to d minus 1 to epsilon. And then for the inelastic process, when I have a damage, I can still assume that this is valid because the damage is changing much faster than the other state variables. And basically, I can define my dissipation as rather than for plasticity, it was sigma times epsilon plastic dot. Here, this is 1/2 sigma d dot times sigma, and plus this term is the same like plasticity, q times psi dot. This is for the hardening variable. So there are two cases, as I said. There's an elastic process with dissipation equal to 0, and these internal variables evolution frozen. So basically, I'm here when I never really left the elastic domain, in which case my d is inverse of elastic modulus, or I'm there where d has evolved towards infinity, so it's bigger, so d minus 1 is smaller. But whatever I do, when I come back, according to this result, that means I load completely with sigma equal to 0, I'll have epsilon equal to 0. So basically, the cracks hypothesis will be close. So this crack closure type of criteria, which is sitting here. So basically, the idea is that how come I have a dissipation? But the fact that I'm climbing here in the inelastic behavior, the path is nonlinear because the change of this d goes from 1 over e to infinity. And you'll see in a moment the tangent is something that looks like plasticity, but e is replaced by 1 over d, which keeps changing. So this is even nonlinear. And then I come back with the linear path, so dissipation is between these two, the straight line here and this bump over there. So how do I obtain the, let's say, this evolution equation? Well, I have to do the case when I have a damage. That means d2, d dot and psi dot are not equal to 0, and sigma is equal to d minus 1 times epsilon, so that the dissipation is defined as 1/2 sigma d dot times sigma plus q times psi dot. And we are fishing for the values of this sigma and q that make the results admissible in terms of damage criteria phi or sigma and q equal to 0. So we're going to go for a principal maximum damage dissipation, which is given here. And basically, I minimize minus damage dissipation, which was just written there. And on top of that, I have a damage multiply gamma dot, multiply the criteria. And I want now to minimize this for any value of sigma and q, because I put constraint on top of this in this Lagrangian, and for gamma also to be positive. So if I take the derivative of the first one, I obtain that d dot is equal to gamma dot divided by the absolute value of sigma. So evolution equation of compliance is given here. It looks almost the same like the other guy, but for plasticity. But remember, there was here a sign of sigma, so it could be the positive or negative, whereas in d dot, it's always positive. So compliance is always increasing towards a infinite value. With gamma dot positive and absolute value of sigma positive, compliance keep increasing with the image. Then hardening variable has exactly the same evolution equation. If I take the derivative with respect to q, I get xi dot is equal to gamma dot. And finally, on top of that, I have my loading and loading criteria. The phi is either negative for elastic process or zero for damage process, and then gamma should be positive for damage and zero for elastic process. So the product of gamma dot and phi is equal to zero. Final step is I have consistency condition. So basically, when I'm at the damage at time t, I want to see what happens at the next step. And basically, the idea is like at the next step, I have to, let's say the only interesting part is when phi of t plus dt is again zero. That will imply that phi dot is zero because dt is positive, phi of t is zero. So this one has to be equal to zero. And that gives me the computation here. Now the only trick is like I need to work a little bit more because I have epsilon equal to d sigma. So sigma equal to d minus 1 times epsilon. So when I compute the derivative, I have like d minus 1 dot. I have to know what it is because I only have d dot what it is. So basically I can come back and mystify this when we come back. But the idea is really like from that one I come to my gamma dot. And finally, go back to the stress rate constant equation to say that sigma dot is either d minus 1 times epsilon dot when gamma dot is equal to 0. That means when I'm elastic process. So initially, d minus 1 is E, or later on, d minus 1 is like a smaller, and I'm unloading or I'm loading in the elastic domain. Or here in this path, you can see d minus 1 times k divided by d minus 1 plus k. So remember in plasticity, there was E times K divided by E plus K. So E being constant, it was always a straight line. But here D keep changing towards infinity. So this is like a curvilinear. So basically, that's really what explains how you can actually build up this dissipation. And this is kind of the representation of damage and what you can obtain for the stuff. And now you can go back and use the finite computation that we've done already for plasticity and simply use it again and work it out. So basically, that is the end of the damage part. So here we come 10 to 15, and basically, maybe it's a time to stop. Where is that one? Resume recording. Good. Already got enough rest. So let's go further. So we have cleared the kind of the damage model, how it works in the way that you can recover more or less all the steps in plasticity model, with the major difference being that internal variable now is damage compliance, and all the other things are just to follow. So the big advantage of recasting damage model in this way is in the sense that we can now couple damage and plasticity. Why do we have to couple damage and plasticity? Well, in most of the real life cases, you take a cyclic loading on your material and you go into the domain of damage, and you can at least observe that both the irreversible deformation, so-called plastic formation, will appear, and at the same time change of the elastic slope. So combining these two materials, like plasticity and damage or material models, you can certainly recover the results that basically the tests are showing. So initial work on that was the work of Lemaitre and Simon Ju. So what they've done is they took this Lemaitre style of model, or Cacciano model, which is taking the damage modulus to be E times 1 minus little d, where d goes from 0 to 1. They have thus produced effective stress. And then they took the effective stress and built a plasticity criteria on top of this effective stress. So intellectually, that means that damage occurs first, introduces the cracks, and then you take the effective stress and you produce plasticity, whatever remains to be healthy material. This is kind of a very special scenario because it doesn't mean that you'll first start with damage. There's really no reason to first start with damage for each and every material. Cracks might appear later in the later stage, and before that you have so-called whatever other type of phenomena which are more prone to plasticity. So we try to put these two things at the same level, not to privilege damage and then have plasticity to be kind of following the damage, but to take any possible scenario, either first damage or first plasticity to occur, and then these two can develop simultaneously. In other words, what you want to describe with damage is a change of elastic modulus, and what you want to describe with plasticity, which is irreversible plastic deformation. can take place simultaneously, and as you go along computing it, there's no reason that these guys cannot go hand in hand, and both changes are done simultaneously. So the idea goes as follows: we took all development of plasticity and all development of damage and tried to couple them together in the spirit that the whole deformation now is cut into the elastic deformation, plastic deformation, what we call damage deformation. This just generalizes a little bit to the plasticity model, because on top of the elastic and plastic deformation, you have damage deformation. Please note that damage deformation is not going to be a new internal variable. It will be only like a navette, what you say in French, some kind of bus that takes you from one station to another, and basically decides how much of the inelastic behavior goes to plasticity and how much of this inelastic behavior goes to damage. How much is one and how much the other is contributing to the total dissipation. Other than that, we just follow other type of the main step that we have for plasticity and damage. Simply do cut and paste. So, for example, if you have a energy type of functional, you have a function which is a function of total strain, or damage strain, damage compliance, damage hardening variable, plastic strain, and plastic hardening variable. Please note now the little d as index is a hardening damage variable, and then little p would be a plastic hardening type of thing. And basically, you can say that this one is a quadratic form in the elastic strain. This is your hardening potential. It could be also for isotropic linear hardening, a quadratic form in the hardening variable, which is let's say a absolute value of the plastic strain. This could be quadratic form of your in damage damage strain, and this could be again quadratic form in the damage hardening variable. These are the choices which are written here, for example. And that's basically how you can define your potential. So these are kind of usual. They could also be saturation potential, things like that. What is important nonetheless is that both plasticity and damage should have the level of the stress that is defined for both of them. So this way, we're going to consider two criteria, one for plasticity, where you take the norm of the stress, and you compare this against the limit of elasticity, and the change of this limit by the threshold of plasticity with the hardening variable QP, which is a conjugate to the hardening variable psi p. And then we also have a criteria for damage, which take the norm of the stress, compare against a limit of elasticity and damage, that's like a fracture stress, and then also evolution of this limit due to the hardening variable QD, which is conjugate to the hardening variable psi d. Typically, if you take this linear potential, if you have linear hardening, you'll have this on QP to be equal minus KP, KP being hardening modulus times Xi P being equivalent plastic strain, and this one would be like minus KD times whatever let's say the hardening variable Xi d. So these are three ingredients that we define. Again, these are just cut and paste from plasticity and damage. We simply copied everything we had. We can also use this like we already done for damage, that we do a Legendre transformation, changing the rows, and basically instead of postulating that epsilon d equal d sigma, we actually postulate that this complementary energy for damage be a quadratic form in sigma. So instead of this guy, we can go for that guy. This is 1/2 sigma d sigma. And then we go into the defining dissipation. Now, total dissipation will be stress power, sigma times epsilon dot, minus the material time derivative of the free energy that we just defined. So now free energy having all these bunch of these terms, you have to take partial derivatives. So when all is said and done, what you have is written here. You have sigma minus the derivative of the elastic potential with respect to elastic strain times the elastic strain dot, plus sigma times plastic strain dot, plus this will be hardening variable QP times Xi P dot, plus here you have a sigma dot times d sigma minus epsilon d, plus 1/2 sigma dot d dot times sigma, and here you have a hardening variable QD times Xi d dot. And so basically, this is the definition of your second principle of thermodynamics. So we have two type of processes First of all, it would be elastic process, where all the frozen, all the internal variables, that would be damage compliance, hardening variable for damage, plastic strain, and hardening variable for plasticity are frozen. That means either they have never started evolution or they had some evolution. We started unloading, so they are keeping the value that they had when they were plastifying or damaging. And for this particular case, we know that dissipation has to be equal to 0. So we cancel these two dP and dd, these two parts of dissipation, because internal variables are, again, the rates are equal to 0. And so from the first part, related to the evolution of the elastic strain, we obtain that the stress is computed as a derivative of the elastic potential. So elastic potential being quadratic form of the elastic strain, you obtain that this is equal to your elasticity tensor times elastic strain. This is how we compute the stress. That really hasn't changed from what we were doing before. And then we also obtained what was done in the damage, that this damage variable, once you know the stress, is a product between the damage compliance and the stress. So damage variable, strictly speaking, once you know the stress and damage compliance, is not a new variable. It's just the way that you define this variable, knowing the internal variable called damage compliance and the stress that is just computed from the elastic strain. Please note that damage compliance, again, it doesn't have to be one-dimensional. It could be in 3D, so we can do damages in shear, in tension, in compression, and so on and so forth. Now, when you have inelastic process, we now assume the most general case, although you can have one or the other being triggered. What will it be triggered with? Well, be with the 0 value of the either plastic or damage criteria. So whatever starts first will start plasticity. So it could be not always damage first and then plasticity. It could be first plasticity and then damage. There's really no reason to say one or the other. It's really the type of criteria which is credible for the phenomena you're trying to represent by plasticity or damage. So considering both of them to be active at the same time, we'll carry on, first of all, by taking these conjugate variables to the hardening variables QP and QD. The first one being conjugate to hardening variable psi P, the other conjugate to the hardening variable psi D. And then we define now dissipation. For the inelastic case, we know dissipation is positive as the sum of the plastic dissipation, which is a product, scalar product between the stress tensor and the rate of plastic strain, and the product between the hardening variable for plasticity and the rate of the psi P, let's say hardening variable for plasticity, the conjugate flux. And we have a damage dissipation, which will have sigma dot scalar product with d dot sigma, and plus QD times the derivative of the hardening variable for damage. Then, when we take this dissipation to be positive, and we want to compute the corresponding evolution equation, so appeal to the principle of maximum dissipation for both plasticity and damage, and we carry on with the constraint minimization problem. That means we take a minus total dissipation. We add on top of that the constraint of plasticity. We take also the minus damage dissipation. We add on top of that constraint of damage. And that allows us to, by appealing to contact optimality condition, to obtain the evolution equation for a plastic strain as a partial derivative of the plasticity criteria respect to sigma times plastic multiplier gamma plastic dot, and hardening variable, again, derivative of the plastic criteria with respect to QP times plastic gamma plastic dot, accompanied with the loading and loading condition that gamma plastic dot should be positive or 0, and the value of the yield function should be negative 0, such that the product of these two, gamma plastic dot and P plastic, should be equal to 0. For damage, we follow the same rule. That is, we take a Lagrangian, which is a minus damage dissipation plus gamma dot times phi b, and we obtain the corresponding contact optimality condition, which allows to write the evolution equation for damage compliance to be equal to gamma d, this should be not p, dot, divided by, multiplied by d phi d sigma, divided by 1 over sigma, and the other guy would be derivative of the xi dot equal to gamma dot times d phi dq. So we have evolution equation that belong to, that have to be specified in terms of the unknown values of the plasticity parameter and this damage multiplier as well. So gamma p dot and gamma d dot should be obtained. The way they're obtained is again with the consistency condition. If at the time t we are plastifying, and we want to keep plastifying at time t plus dt, that would imply that the derivative with respect to the pseudo time describing the particular loading program of Vp, the plastic criteria, should be equal to 0. And that amounts to saying that you have a derivative of Vp with respect to sigma times sigma dot plus derivative of Vp with respect to Qp times Q dot. So sigma dot is equal to C elastic times epsilon dot minus epsilon damage dot and minus epsilon plastic dot. And epsilon plastic dot, we just had it, is basically equal to gamma plastic dot times d phi dq. And basically from that one, this equation we can easily obtain if you keep linear hardening, isotropic hardening. We saw that it's only a single linear equation. You get your plastic multiplier to be equal to a derivative of d phi plastic d sigma times C elastic times epsilon dot minus epsilon damage dot divided by d phi plastic d sigma, the elasticity tensor CE times d phi plastic d sigma, and here would be d phi plastic dq times the hardening modulus K plastic times the d phi plastic dq. So this allows us to write stress rate equations that could be either C elastic times epsilon elastic minus epsilon elastic dot, epsilon damage dot, if you have an elastic process, or it could be elastoplastic modulus, which is here, C elastic minus C elastic times d phi d sigma C elastic divided by this scalar term d phi d sigma C elastic d phi d sigma plus d phi dq times the hardening modulus of plasticity times d phi dq. And after that, we take the consistency equation for damage. In other words, if at the time t, we are damaging, and if we want to keep damaging at time t plus dt, that would imply that time derivative of the damage criteria of Vd has to be equal to 0, which amount to saying you have a d phi d sigma times sigma dot plus d phi damage dq times q damage dot. So we already said that the time derivative of this one was given here. Basically, that I can plug this into the equation and obtain my damage multiplier to be equal to d phi damage d sigma d minus 1 times epsilon damage dot divided by this scale term, which is d phi damage d sigma d minus 1 d phi d damage d sigma plus d phi damage dq damage times the hardening modulus for damage times again d phi damage dq damage. So this way I have actually two of these guys computed, and I can write again my stress rate equation for the damage to be sigma dot equal to C elastic damage times epsilon damage, where C elastic damage is equal to say minus 1 when you never really started the damage, or goes to this reparation to d minus 1 and so on with the modification here when you started the damage. So now I have two expressions for the sigma, one coming from plasticity and one coming from damage. And now I want this two expression to amount to the same value, because plasticity and damage have to keep sharing the same stress. There's the hypothesis of our model. So basically, you have a stress rate equation for plasticity, which says that C elastoplastic times epsilon dot minus epsilon damage dot should match C elastic damage times epsilon damage dot. So from this one, I can compute that epsilon damage dot can be obtained as a C elastoplastic plus C elastic damage to the minus 1 times C elastoplastic times epsilon dot. So, and all said and done, I'll take this and plug it back into either one of these equations. I obtain that sigma dot is equal to C elastoplastic damage. Tangent modulus could take into account both plasticity and damage, and multiply by the total strain epsilon dot. And so C elastoplastic damage is equal to C elastic damage that is provided here, multiplied by C elastoplastic plus C elastic damage. C elastoplastic is provided here. All this inverse, again, times C elastoplastic. So this elaborate computation, but there's no reason that you cannot do it. So what is the graphic illustration of this? You can see that contrary to the case where you have to start first by computing the effective stress by using damage model and then apply criteria for plasticity, here I illustrate the case where first plasticity will start. Simply that means that the yield stress is lower than the fracture stress. So plasticity will start after you reach the value of sigma equal to sigma y. And after that, you have a case where the you climb up here with the constant elastoplastic modulus. So this would be E K plastic divided by E plus K plastic, where E is Young's modulus and K plastic is hardening for plasticity. And once you reach the value of the fracture limit, then the damage kicks in. So this, strictly speaking, is not straight line anymore. It's a curvilinear because damage compliance keeps increasing. And C elastoplastic damage is the one which is provided here, where it depends already on the value of the damage type of thing. So you keep loading up to a certain level, and then you start unloading, and basically recognize that when you unload, you recover here the first part would be elastic strain. What is here irreversible, it's a plastic strain. And basically after that, you have a damage strain. So this gives you a really very clean illustration of what this model is capable of doing in order to provide the whole type of response that you might want to compute. That's really the idea. So really, I mean, just setting these limits of sigma y and sigma f any way you want, and picking up the right criteria, you can keep getting any result that you might want to obtain. Maybe it's a good idea. We can go back to a little exercise just to see what it is. And basically, if I have this, let's say a bar, and I'm soliciting this with a sigma, and my behavior would be described with let's say up to here, sigma y, and then sigma f. And after that, I keep having some kind of nonlinear response. So I have to define the parameter which are Young's modulus, okay? Then sigma y and sigma f, when these guys start yielding and damaging, then I have to define my hardening modulus for plasticity, and I have to define my hardening modulus for damage. So I let you choose all these values and try to get, let's say this is cross-section A, so here instead of providing sigma, I have a T bar, which is equal to sigma times A. So imagine if I'm pushing this into the value, it goes from, this is T and this is T bar. So it goes to 1.5 times sigma, I don't know, let's say which one is bigger, sigma F times A, okay? And that will be simply linear. And then you unload. So I want you again to have a computation of the final state. What is sigma in this case? And what is the plastic strain when you unload it? And what is damage compliance? And what is the damage strain? All these things could be computed, okay? This is another nice exercise where you can kind of demystify all this to see what we were talking about, okay? So here's a couple of simple numerical examples. We were doing this with, let's say, for means criteria. There was very well-known work by Gerson, who was working with Needleman and Twegart at Brown University. These are well-known guys in material science. They wanted to study like porous metals, and where you have this porosity. So they did homogenization, the final scale, and changed the J2 plasticity criteria with had only like von Mises criteria by adding some kind of extra term, which has to do with the first invariant because of the porosity. You have a change of volume and stuff like that. So instead of such a plasticity criteria, we decided that the porous method could be treated by taking into account like a plasticity of the matrix, and then the pores would be something like a damaged type of material, which is filled in with the softer tissue. And then, for example, if the damage of this material is prone to a change of volume, so we can take a damage type of criteria to be related to the trace as opposed to plasticity, which is related to the rhetoric part, and compare this against the damage value and so on and so forth. And then both of these were like some kind of a saturating hardening type of thing for one and the other case. So we ran this simple tension test with a plate with a hole, and then basically for the plasticity, you take a typical pattern of failure, which looks like a J2 plasticity. You have these shear bands at 42, 45 degrees, sorry. Whereas when you have a plasticity and damage, it doesn't really matter into that. But maybe I can show you the things that we are really doing a little bit more in detail. For example, there was the work that we are doing with my former student, Adnan Ibrahimbegovic, who was then working for Plasticity de France, now working for this European Research Center in Israel. Basically, that was a new look at the cap model, which is typical of many of these cohesive materials. So what is cap model? You have like the model, which is take into account, for example, like geomaterials, where you have like a pores. The porosity of geomaterial is well known. We also then applied it to the same thing with the versatile type of material with metals and alloys, which are porous. So we treated this as a two-phase media, where like there's a matrix and there are pores. So matrix is handled by the plasticity model, and pores were handled by the damage model. So the first one, we took this Drucker-Prager plasticity for cohesive materials. This is like a typical. So earlier work was a former student of mine, Samir Dolarevic, who worked on the model for soils, where we took a Drucker-Prager type of criteria to describe the sliding of soil. This is characterized by the cohesion and the angle of internal friction. The easiest criteria of this kind is so-called Mohr Coulomb. You simply say that tau, being the shear stress, is proportional to tangent phi being a tangent of on the angle of the internal friction, times sigma n being the normal stress, minus C cohesion equal to 0. If you want to generalize Mohr Coulomb, which is kind of one-dimensional, to a three-dimensional case, you replace cohesion with the square root of J2. This is square root of the rhetoric part of stress. And you replace normal stress with the first invariant of your stress tensor. And then you adjust the coefficients accordingly. Now you get this line, which is given by the angle of general friction and cohesion, to handle the sliding of this material, like soils and stuff like that. On the other hand, you have to take into account that plasticity would happen also when you reach certain tensile strength, and also when you reach certain compressive strength. So in tensile strength, we put one cap, what is called, and in compressive strength, we put another cap. And so initially, what we are doing, we are putting kind of a three surface plasticity with the Drucker-Prager plus the two caps. And then this caps in compression was also taking into account like a compressive, let's say, deformation. So when you're compacting the soil, it becomes more and more resistant, so hardening phenomenon. Now, initial approach, the paper that we wrote with Dolarevic was basically that we took this three surface plasticity, we turned it into a single surface. So this way you can go into the standard framework with a single surface plasticity to do computation. Nonetheless, there were like three different regimes that you have to take into account to compute real behavior. So it just kind of on the first glance, it simplified the problem. In reality, it hasn't really simplified that much in terms of computation. Anyway, then we realized actually the more credible thing would not be to turn this only into plasticity, because the porosity of the certain material would actually mean that when you're doing some kind of let's say, a loading that goes beyond limit of elasticity, you should have a change of the elastic response. So instead of this, we actually combined damage and plasticity. In other words, we kept for the sliding the plasticity model, which is related to this Drucker-Prager yield function. And then for the damage, we simply took these two cutoffs that are proportional, let's say, to the trace part, and then basically combine this instead of these caps. And so this way we are able to see Prager is if one means is his illustration is a cylinder which is put on top of this hydrostatic axis being the value of the hydrostatic pressure, which is perpendicular to the electric plane. Drucker-Prager has something like a cone type of behavior, where basically it gets bigger and bigger as you go away from the deviatoric plane. So this then allowed us to do coupled damage plasticity model, where both of these things were allowed to harden And basically the idea is that you can then compute the combined, let's say, inelastic behavior from the plasticity of the Drucker-Prager plastic sliding and the damage from the compaction. So the elastic domain for it's rather simple this way. You can have a straight line for the Drucker-Prager. If you take a representation, the square root of J2, the second derivative of the dirichlet stress, that's the normal dirichlet stress, and this is the first derivative of the stress. This is the trace of the stress tensor. So these are just the elastic domains basically bounded by these two straight lines. Then we had to define the free energy as a sum of the contribution from the elastic part, plastic part, and damaged part. Then we already explained these two plasticity and damage criteria. Then we appeal to the second principle of thermodynamics to get the total dissipation and to get the corresponding evolution equation. That amounts to saying that here we have a total strain to be sum of the elastic, plastic, and damage strain. And the stress is basically computed from such an equation by taking only into account elastic strain, and the damage deformation is computed not as a new variable, but with a known value of stress and the known value of the damage compliance. So he ran plasticity model, we run damage model separately, and then we compare the value of the stresses. The way it is done, you have a global loop computing the displacement at each and every node. This is iteration I. Then you might have a Gauss point integration loop, which is required to do plasticity computation and damage computation. If you have a linear hardening, it's just one iteration, but if you have saturation, non-linear hardening, this requires iteration with the J loop. And then on top of that, for the coupled damage plasticity model, you will require a K iteration at the level of the whole element, because what you do is you set initial guess for your damage deformation. Then you go to separate computation for the plasticity and damage by splitting what goes to plasticity, what goes to damage. And you provide this value of stress at n+1 by the plasticity model and the value of stress at n+1 by the damage model, both of them being admissible in terms of plasticity criteria here, admissible in terms of damage criteria, so they have full admissibility for both criteria. And then I compare this value coming from plasticity, this value coming from stress, from the damage for the stress. And if these values are not small enough, I mean, the difference these two values is not small enough, beyond the tolerance that I choose, then I have to do another iteration of the damage strain, which follows from basically computation that we've done here. I know, so it's on this one here. That basically is like giving you how to compute this this type of thing in the damage model. So basically, the idea is that I can have the computation of this kind, and at the end converge into the. So one illustration is like a soil mechanics type of problem with a flexible footing. So you have your type of structure here sitting on the soil, and they have deformation, and you can get, for example, the loading and unloading curve. So if you have plasticity, it goes up until limit of elasticity, then unloads with a parallel type of response to the elastic loading. If you have damage, it goes up and it goes down differently with a straight line going down to zero. So this is plastic dissipation, this is damage dissipation, but you have both plasticity and damage, you get this green curve. So you have both irreversible deformation and you have a change of the elastic response. We have also done it for these porous metals and alloys that I just described previously instead of Gerson criteria, which is written here. So like these coefficients C1, 2, and 3 that come from homogenization at the final scale. They have the rhetoric part, there's trace part, and compared against sigma y. Basically, you have this one in this setting where basically is a what you call it, if you look only plasticity, but if you now take the pores are filled in with damage, so you come back with the damage criteria, which is proportional to the trace part of the stress. And then this is your classical J2 plasticity. Basically, then the elastic domain becomes very simple, it's rectangular in the space of these square root of J2 and I1 invariants. So it becomes a rather simple computation. that we're able to carry out and get these results. Okay. And again, there was I showed this result before. If you have only plasticity, a typical failure for this simple plate with a hole that corresponds to J2 plasticity with a shear bands at 45 degrees. And if you have damage, these things are changing a little bit. Now, the whole point, if you are using this approach, you have this key extra loop is the one which has to do with the iteration at the level of the element to combine the stresses at one and the other model, and basically that you have to have like a iterative values of the damage strain that has to be updated constantly. So this is typical result that we obtain in our computation. Initially, you can see the difference between these two stresses could be quite big. If one kicks in and doesn't, you can see the order 10 to the power 17, 12, and so on and so forth. But when you go into the correct value of the damage strain, it starts converging quite well. And you can see here that the damage strain already, which is converged up to what is 2, 4, 6, 8, 9 decimal points. This norm is still very large, so you need to go even further beyond that in order to get this result. Well, maybe here there's some discrepancy in there, but in any case, like the fact that you have to iterate, extra iteration is also extra weakness, I would say. So this advantage of this model is that you can have a coupled damage plasticity, and you can obtain description of the behavior of real-life material, porous material, in a better way by using the kind of porosity related to damage type of model. Disadvantage is that you have extra iterations and that you have to worry about the convergence of these iterations and whatnot. So basically, there was another the doctoral student that also had to work on that. That was Pierre Géel, who is now lecturer at École Centrale de Paris. So basically, what we've done with Pierre, we were studying the dynamics of something like a concrete-like behavior. And if you look into the experimental results, which are available in one of these theses, I think it was in Saint-Léon by Daoud and stuff like that, he was doing compression tests with the cyclic loading, with dynamic load, and was able to record different stress strain diagrams. So this is your typical behavior in compression of concrete. You start basically here and you keep increasing the values. So you can see at certain point, you will have a residual deformation, bigger and bigger as you go along. And you will also have a change of the elastic response as you go along. And even like there's this, you go to the peak value of resistance and you go down to softening. And we talk about that in the kind of next step as you go along. And in order to be able to reproduce this, we had to combine lots of, let's say, models. We actually put together the viscosity and then plasticity and then damage, and even the one in softening. I haven't talked about that, but in the end of the chapter 3, you will have it basically as we go along. So these different criteria allow us to have a definition of many of these internal variables. So if you want to take into account such a very complex behavior in cyclic loading, you have to line up viscous deformation, plastic deformation, plastic hardening variable. This was, I think, lambda p was, I forgot now what it was. It was, I think, for kinematic hardening. And then there was a damage compliance, there was a damage hardening, there was a jump that is related to the softening part, and there's a softening variable that is compiled there. So each and every of these internal variables are 2, 4, 8, 2, 4, 6, 8, has a conjugate stress that is driving this variable. So what we were really aiming at, these are true experimental results. And you can say that this happened at the scale which is sufficiently fine to be considered homogeneous. And then basically, for us, we want to get a boundary problem where this is just represented to a single point. So the main goal for us was to be able to represent a typical dissipation that is taking place in one of these hysteresis loops. So hysteresis loop being this nice eggplant type of shape, you can obtain a corresponding area. And then in order to make our computation robust, we took a linear hardening or linear softening, which amounts only to one iteration. You're sure to converge. And you do not reproduce the shape of your hysteresis loop, but the goal of identification was really on top of the shape to also get something like a area. Because shape was much less important. We don't care about shape. Anyway, we cannot reproduce this linear shape unless we take nonlinear hardening and softening and so on and so forth. But we can reproduce the area of a particular loop and represent this with kind of rhomboid type of structure. And obviously here you have many variables, you have many parameters to define such a model. So the question of how to identify these parameters is certainly very important. Our idea was to split the identification to a certain number of these steps. So first you identify when you actually start the plasticity, then you identify when you start accumulating the damage, then you identify what is the ultimate stress you go for, then you start identifying what is your, let's say, plastic deformation, what is jump in plastic deformation, and so on and so forth. In any case, you have to have a very elaborate experimental program to be able to feed into such models. But let's say you're able to quantify all these parameters correctly, and you can feed into them. Now, let's see what you can compute and how to compute that, given that the previous computation required a very elaborate iterative process, which is sometimes starting from very large difference between what plasticity and damage gives you. So the risk of not converging is quite significant. So in order to eliminate this type of worry, we have worked out on a little bit different approach. First of all, this is the type of problem we try to solve. Now, given these 8 internal variables, we have to devise 8 evolution equations, which we've done here. There's an evolution equation for viscous deformation. All of these evolution equations have been written previously, so you just have to go to the proper page and do cut and paste. Strictly speaking, nothing has been invented, it's just combined all together. So we have this evolution equation of viscosity, you have the viscous deformation, evolution of plastic deformation, of hardening variable, and then of this kinematic hardening. Then there's a evolution equation of damage compliance, evolution equation of the damage hardening. Then you have this, the let's say, softening part, which I haven't really discussed, but I will eventually in the next lecture. And basically also the softening variable. And what was really the goal? The goal of us, of our work, was to be able to replace interpretation of damping and go away from something called Rayleigh damping, which is typical of many simplified analyses in dynamics. Rayleigh damping is a choice of the damping matrix. First of all, damping phenomena is related to the rate of deformation. And basically, you have a damping matrix, which in Rayleigh damping is restricted to be a linear combination of the mass and stiffness matrix. And then you can work out the model analysis is typical of linear analysis. Having chosen a damping matrix to be a linear combination of stiffness and mass, you can obtain your eigenvectors that are the same as undamped vibrations. That doesn't change. And then you can write your model equation, which featuring now damping coefficient, psi, which is defined from mass and stiffness matrix, a contribution that is coming from the mass and from the stiffness. Now, what this type of Rayleigh damping can do, it can give you the level of damping, which is typical of, let's say, interval of frequencies where the structure is going to be responding. And you choose typically something like, at least this was a work choice for many engineers over the years. You have something like a 2% for steel structures, 5% for concrete structures. Nobody explained what L is 2 and why is 5, but anyway, that's the way that you do it. But if you look into typical response on the earthquake, you basically have a very mild response for something like a viscous internal variable will take into account. Then you have this strong shaking. And in typical computation, this Rayleigh damping will cover this strong shaking. And then you have this free vibration of the damage structure, which is not necessarily the same as the free vibration of structure which hasn't been damaged. This is more like a friction type of phenomena, and this is more like a, let's say, viscous type of phenomena. In fact, actually, the only good thing about Rayleigh damping is the fact that the amplitude decay is exponential, which has been observed in many of these tests. And you can kind of fit your oxide to get the proper exponential decay. Whereas if you have plasticity or damage, the amplitude decay is linear. You can have this analytical solution. There's many books that give that. So if you now have this at least three phases of the earthquake response, that is a mild earthquake and the strong earthquake shaking, and then free variation of the structure, there's no way you can just take two coefficients in the Rayleigh damping and obtain the proper description of these three phases by that. Whereas this model certainly can do that, but you need to have many, many variables. Again, once you can do that, you want to see, because this viscous will take part of that, this will take care of the strong shaking, and then free vibration of the damaged structure will be automatically also respected because you have this damage sitting in there and so on and so forth. So the way to keep the computation efficient was as such. We actually took a beam model and we built a multi-fiber beam model in 3D. A typical representation would be like a fiber reinforced composites. In the application we were looking at, there was like reinforced concrete. So the black fiber is steel and the white fibers is concrete. And then we have worked out, this is your Ole Bernoulli beam. We have a displacement in every fiber to be displaced on the neutral axis of the beam. U field of x and t minus ZF. ZF is position of the particular fiber with respect to the center of the cross section times dw dx, w being the transverse displacement. And then when you have a breaking, you have a Heaviside function minus a function which is describing how the crack dies off from this point where it is introduced. Typically, this is taken in terms of the shape functions of particular elements. We'll talk about that in a moment. Well, next lecture rather. And then times the jump, the crack opening or particular stuff. So these here are equations of motion that are built from a contribution of each and every fiber. So basically, you're having a weak form. You're integrating over the length of your beam. This is the inertial term that you have here, like rho times the cross section of your particular fiber times the acceleration multiplied by the rotational displacement here. Pierre used this lousy notation calling this delta U because there are many symbols. So at a certain point you kind of yield with the facility. And this will be your virtual strain, that is the derivative of the virtual displacement that we called here delta U. This is like W, what we called before, but there's already W here. So you cannot run always too many of these notions to the same letter, times the fiber. So this is fiber by fiber. You take into account all the contribution, and you get your equations of motion. And on top of this equation of motion, what we've done here, we basically split the total strain into the elastic and then plastic and then damage type of thing. And basically, this is the kind of thing that you can have enforced here with a Lagrange multiplier that is typically the stress in the fiber. And of course, this has to be constrained to admissibility with respect to all these criteria that we had to choose with like viscous criteria, plastic criteria, damage criteria, softening criteria, and so on and so forth. In agreement with these criteria, every time there's a particular multiplier, either viscous, plastic, or damage, it has to be positive 0, and particular phi has to be negative and 0. Okay, so basically this is now something with the unknown displacements other than internal variable and stress, like you have here. So what we have done here, we have introduced the direct interpolation of the displacement and direct interpolation of the stresses. So it could be quite easy to do that. If you have, for example, a two-node transparent element, I can do that. Let me maybe illustrate that. That will be good for homework. I was giving you homework before to do this coupled damage plasticity. So why not try this? So I have my bar, and I have a behavior which is like you have a yield stress, and then you have fracture stress, and then you have this one. So this is sigma y, and this is sigma f. And this is, let's say, some kind of value here that you can take both plasticity and stuff. And then basically I can introduce my interpolation of displacement field by taking this shape function that goes from 1 to 0, and then from 0 to 1. So basically I have a displacement field u of x to be equal to n1 of x, which is 1 minus x over L, times u1 being the displacement of the first node, plus n2 of x times u2 being the displacement of the second node. So this is 1 minus x over L. And this is your x over L. And then I can take sigma x. An easy way would be here to call it some function, what you call it m of x. So it could be this one times beta. So beta is stress parameter, and the simplest choice, so this one will be simply 1. So basically, now I can define my interpolation. I have to have a hybrid stress approach. I have to find, for example, this P would be equal to, in this particular case, integral over L, 1/2 du dx times, I'm talking about elastic response to start with, E times du dx. For the moment, I ignore all these internal variables, minus P external. And then instead of this total Hoover-Schitzer principle, I can go to something called Hellinger-Resner principle. H like Hellinger, R like Resner. So you go into the same integral, but here will be minus 1/2 sigma times E minus 1 sigma, then plus sigma times du dx minus P external. What is the difference? The unknown value here is just displacement, whereas here the unknown values are both u, displacement, and stress is sigma. So when I compute the variation, I will have two equations, and I have to do interpolation. Of course, when I have now inelastic behavior, I have to add all the other guys to go for that. So you can try to do this, what I was giving you to go to the fraction, which is 1 point, t bar to be equal to 1.5 times sigma f times a whatever, to be like at least 50% larger than the larger fracture stress, and you choose all the coupled damage plasticity, and you check what happens, how more easily you can get it when you have a stress type of interpolation, just to kind of demystify this, what I'm telling you about in this particular case, okay? So basically the idea is that I can run this computation this is my equation of motion. Here's inertial term, this internal forces that I obtained from discretizing this, and these are external forces, and then extra term will give me the definition this time around, not of the tangent stiffness. You can say for any particular element, you can have this displacement, and you have this extra term for your stress parameter. So in fact, when I look into this structure of my element, it turns out that having chosen stresses in turn is independent variable. It will allow you at the first time not to compute elastoplastic tangent stiffness, but elastoplastic tangent compliance, and also the damage and so on and so forth. So the big advantage of that, all these terms are directly additive. So you can go very easily and you carry out computation of all these terms. You get corresponding influence of the internal variables, and basically you get corresponding response, whether you are hardening or softening or so on and so forth. You sum it up into this H, and then from this one you can get, let's say you get inversion. This becomes H minus 1 G times G transpose. and you get your stiffness matrix. So that becomes very easy. This is just a linear computation. And then basically on top of your, let's say you get the corresponding value of the stress parameter, and you can carry on this computation of the motion equation by feeding into the external force from the corresponding stress. So basically, you can even take into account viscosity. So that is just modification. You have a viscosity take into account. And again, this is the type of experimental result that you get. And what we reproduced by using our model is this diagram over here. So you can see that this nice curvilinear hysteresis loops and these piecewise linear kind of rhomboid type of structures are not the same in terms of the shape, but at least we try to have area on each and every of these loops to be as close as possible. And also to reproduce the salient features when you have a, kicking into the damage and kicking to softening and so on and so forth. So if you take a simple loading program, you can see difference in shape, but not necessarily in dissipation. But typically, recall that what we are really running is some kind of stochastic loading, which varies in time. And in fact, for this type of loading, if you want to talk about safety, you better just be able to prepare like an estimate of the, let's say, performance of the structure in terms of whether you are over the board or you are not. And that means that you're going into softening or not. And then you can get a little bit better estimate of the safety. There's another thing I said, when you're having this type of response, in the beginning, the viscous response is quite credible, but at the end, you have like a right friction, the damage structure would have this, let's say, frictional effect on these cracks and so on and so forth. So you have actually, here would be like something that is exponential, and the other one would be like a linear amplitude. You can improve that because, as I said, what is the most credible about Rayleigh damping is that you have an exponential decay of these amplitude as you go along. So basically here, we were able to reproduce that. The idea goes as follows. If you now take into account that your material is not homogeneous, but it is heterogeneous, and then we can say that the yield stress of the plasticity part of your model is not characterized by a deterministic value of the yield, but it could be something like a random variable, or if you want even more complicated random field. That means you have let's say the simplest case would be Gaussian distribution of your yield variable. And basically you can say if the structure is very homogeneous, the standard deviation, that means the Gaussian distribution is characterized is a very famous bump. Even those who don't study probability, they know about the Gaussian distribution. So basically, you can say the average value is the one that you cite when you talk about deterministic, and then standard deviation is how much you're off. Let's say 5 or 10% off in your estimates. So Gaussian distribution, which has this exponential description of this probability distribution, is characterized precisely with these two values: the average value and then standard deviation. So if you have this type of result, and we'll talk about that basically when you have real life material, but often it's not Gaussian, but whatever, you can start with this one just for illustration. If you have a very homogeneous material, in other words, the standard deviation is very small, you can see that the decay is pretty much linear. But on the other hand, if you have a highly heterogeneous material with very large standard deviation, then what you get is this linear response varying from point to point, and then they accumulate, it start looking more like an exponential response. And so basically you have something that is really like a decay of the exponential that is a kind of much closer to exponential results. But the result itself is very important because the idea is that when you're identifying Rayleigh damping friction damping coefficient, basically, you have to carry out a result on a particular structure. Your particular structure is characterized not only by particular material, but also geometry, cross-section, and so on and so forth. Because you need a stiffness matrix, you need mass matrix in order to compute your eigenvectors, and so on and so forth to get your model equations and whatnot. So every time you change the structure, you have to repeat this test for the real-life structure, which is certainly not easy. On the other hand, here we can do the test on the material, like this thing has started. Really, these are kind of material tests that we came. And then basically, if you really want to reproduce what happens at the level of the structure, you can quantify the, let's say, heterogeneity of particular structure by the something what we call correlation length and stuff. You'll talk about that. And then basically that gives you the possibility of describing the true behavior in a more realistic way. And it turns out that once I have identification of a material parameter, plus I have quantification of the heterogeneity of my real structure, which is characterized here with the standard deviation or variability of the yield stress. The more it's heterogeneous, the more there's variability of the yield stress. You can start recovering something which looks like a proper decay, whatever is the size of the structure. So you can hope that basically you are able to do the tests once for all, and then extrapolate this to different structures as long as they're built of the same material. I have to say this is a really high hope, and then basically if you really want to do that properly, you have to take into account something called size effect. Namely, if you have a composite material and you're able to do testing on a small specimen, you cannot be sure that the result from the small specimen will be the same in terms of failure and fracture pattern and so on and so forth, like in the large structure. Typically, again, this is easy to explain by probability, because if you have a composite material which is heterogeneous, that means from one point to another, the results of the material behavior might be changing. In a small structure, you're likely to be homogeneous. In a very large structure, you might have weak spots, either initial defects or induced defects by the loading. And so these defects are prone to producing the fracture much faster than the one that when you have no defects. So the bigger the structure, the bigger is the uncertainty about these defects. And typically you have something size effect. The size effect meaning that then you're having a specimen which is small and you establish the ultimate load. It's very likely in a very large structure, the ultimate load will be not the same. And the bad news is on the very large structure, the ultimate load will be small. So we have also worked out these probability estimates on the computing the ultimate load on a very large structure which cannot be tested. And these structures which cannot be tested in real size are ample. You know, recently you had I was really glad that in European companies do not have this Boeing 737 MAX, because this, I think, already third disaster. First one happened in Indonesia and went down, but many Indonesian companies, I was there 2 or 3 times as invited professor, what they call world-class professor, visiting University of Jakarta. And then I would use a weekend or 2 to go to visit nice place in Indonesia. And every time I was afraid taking these flights because the record of accidents of these private companies in Indonesia is very poor. So the first time Boeing 737 MAX went down in one of these Indonesian companies, everybody said, well, it's just the fault of this company. Then supposedly Ethiopia is a little bit better company. So the second time, very soon after the first accident happened, then they say, well, it's no longer a problem of a company, it's a problem of the airplane. So they found that some kind of software is not good. And now the recent Alaska Airlines that had the door falling off and stuff like that, this seems to be not all problems. So 737 had been solved. So unfortunately, you could never take the whole 737 and crash it into some kind of test. And more importantly, it gets damaged because of turbulent flight, not because somebody is doing static testing, whatever, at the end of doing this stuff like that. So since you cannot be testing this in the real size, then you have to rely on the test on the small size specimen and then extrapolating these results to the real structure, which always have these doubts in terms of handling properly the size effect. That means, you know, getting the real structure estimate failure as opposed to this one. So basically, this was the idea. So let me share this one here up. When I go into this one as a kind of conclusion, what we have done in this lecture about inelastic behavior that we were talking about yesterday and today. First of all, I introduced thermodynamics with the main reason of rigorously defining dissipation by using the Sankara principle of thermodynamics. And basically, this can allow us to talk about the main, let's say, product of the inelastic behavior, which means that all the energy doesn't have to be stored and then recovered like in the elastic case. it's actually dissipated and it's lost in the process. In fact, you can even observe dissipation in many different ways. When you have a plasticity, you take a paper clip that you put together these pages, and you start, torturing it with cyclic loading. And if you keep your hand on this clip while you're doing it, you can feel that it starts getting warm. Typically, this dissipation is often really related to releasing the heat. For the quasi-brittle material, that's much less, and you can really not take into account this correctly. But in any case, quantum dissipation does require thermodynamics, which you've done to start with. And then I say, okay, forget about temperature, and then we kick it out, and we just use this dissipation definition without worrying about temperature. You can come back to that, and there's actually chapter 7, which does it. Then I have taken a 1D plasticity model to explain all the way how you compute. So basically, it has always 3 main ingredients. It has a total strain split into the elastic and plastic. It has a free energy function R, typically to quadratic form elastic strain and hardening variable, the simplest case, which require you to define whatever Young's modulus and hardening modulus. And then finally, the defined yield function, which has an absolute value of sigma compared to sigma y. So you have to define yield stress, and then eventually you can go to threshold, which is K times psi being the equivalent plastic strain. So these 3 main ingredients, then you go back to second principle, you define dissipation for plasticity sigma times epsilon plastic dot. For damage is 1/2 sigma times d dot times sigma. And then basically you can appeal to the maximum elastic or maximum damage dissipation to obtain these evolution equations. The evolution equations are expressed in terms of the plastic multiplier or damage multiplier, which you compute by appealing to a consistent condition. That means time t if you're plastic or if you're damaging, and time t plus dt. If you want to keep doing that, then you have a contribution of the plastic multiplier or damage multiplier, and that allows you to do this computation by asking that time derivative of the yield function or time derivative of the damage function be equal to 0. You obtain your gamma dot for plasticity, your gamma dot for damage, and then you go back to a stress rate equation. You show there are 2 regimes. There's like a regime which is elastic, one thing happens, and there's a regime which is inelastic, either plasticity or damage. And then we managed to build both plasticity and damage into the same setting. Then I took plasticity and I showed you next to this 1D case, the 3D case for Mises is rather similar, other than using the bold-faced letters, because a single stress component is replaced by stress tensor, single strain component is replaced by the strain tensor, and so on and so forth. And the reason you have these strange coefficients like square root of 2/3 and stuff like that appearing, but other than that, I'm still describing the same physics. Basically, then we follow this type of steps that we done already traced in 1D setting. That is, you compute your whatever internal variable from over single steps t. And basically by using this trial step where you first assume that it's elastic and then you go and to correct if it's not. And the process you get the final value of stress and the final value of the elastoplastic modules. Then you go to global, you redistribute the stress, you see one of these elements yielded, and you go back again to the global displacement and so on. So to local computation for the Gauss point, and that's it. So the fact that both damage and plasticity have been cast in the same format allowed us to, I would say, rather easily combine plasticity damage. It simply repeats all these steps, but so it's really again the same. It just has many more of them. So at the end, the one that I showed you with Piaget, there was like 8 different variables because it took into account viscosity and plasticity and damage and then softening. But that describes quite nicely the whole damping phenomena when you have instead of really damping, you have much more credible description of something that looks like actually. I've been at Berkeley. I studied this because there were very good professors like Clough and Wilson, stuff like that. And in California, earthquakes are important. When I was there was really sadly famous 89 earthquake where 200 people got killed and lots of damage in San Francisco and everywhere. But then I didn't work on that for 20 years. And then I was invited by colleagues from Slovenia in one of these workshops that were handled between US, Europe, and Asia. And I met everybody who is anybody in this earthquake business after 20 years. And I came with this material type of justification. So initially, when I saw what they're doing, they were arguing whether it's displacement-based or stress-based or force-based criteria is more pertinent. It was really kind of very much simplified models. At that time, many of these design codes that are built many years ago. And basically, I said, well, this should be neat. There should be really like a energy-based type of criteria. That like a logical thing how you can guarantee the safety on some kind of long-term, let's say, loading processes. You say that the accumulation of the damage in this long-term process has to be sufficiently small that the structure has the ability of dissipating. And then you're sure that your structure is safe. But then it requires computing this dissipation over a long time and being much more credible in terms of, let's say, dissipative effects. So initially, as I said, when I gave my lecture, then everybody was first shocked. But then many of my former classmates said that I'm a good student. And then everybody from Asia and US was coming to say, can we collaborate? But what the hell, I said, you cannot collaborate and everything. In any case, this is something really one of these domains that could be revisited. You have similar thing with the, say, fatigue failure, because many of these things you can have in mechanical aerospace engineering, because all these airplanes, they have cracks. So it's just the question whether these cracks are stable or not. So taking linear fraction mechanics to say the stability of the crack, I would say certainly it's not serious enough, because it depends on the history of the plane, how long it has been flying, how long it has been through these tough conditions, and so on and so forth. So one really has to be able to observe this at a very fine scale and take into account this kind of, let's say, the things that basically, maybe to complete this, although this is the subject of chapter 8 or chapter 9, I'll probably do this tomorrow, because I make a jump. What I was teaching about today was all in chapter 3 and yesterday. So the first 2 days we had chapter 2 with elasticity 1, elasticity 2, 2D and 3D. And then yesterday and today we had chapter 3. So right now we are at the stage of covering first, let's say, 300 pages. And I hope that during the weekend you'll have a chance to read it and learn a little bit more. And you have a chance to grab the book and start it. So we'll do that tomorrow for this softening part and fracture and failure, but with a couple of minutes left, there's no point of starting right now. And the final word is like when you do the computation, if you take J2 plasticity, the final term interpolation have to be chosen with care. Namely, you have to have this handling this locking phenomena related to quasi-incompressibility, given the application with the plastic strain is much bigger than the elastic strain, given that the plastic strain with Fermi's criteria is incompressible. That means that total strain is quasi-incompressible. So usually finite interpolation, for example, constant strain triangle will be very lousy for plasticity computation for measures, that's for sure. And then you have to do something better. But we'll see also how to do enhancement when you go into dynamics and things like that. So this is roughly what I wanted to say for today. And tomorrow we'll take this step to the kind of fracture and stuff into the and try to build on top of it. Okay.